All right, so Unit 3, Electrical Electronic Components. What we were just saying is if you are working on a vehicle and let's say you have a theory of what could be wrong, the first thing you have to be able to do is identify like what components are in the circuit. So let's say we were talking about that wireless charging issue. I don't really know. That was on a 2020 Ford Transit Connect. I don't know what's on that circuit for the wireless phone charging. I have no idea. So one of my first steps would just be, I'm going to pull up a wiring diagram, and in the wiring diagram it's going to have some symbols. And most of the symbols I'll know. Some of them, if it's something that I don't see real commonly, I may have to reference it. So this is just a shot of like a glossary of terms and symbols. So if you see a symbol and you don't know what it is, somewhere in the service manual there will be a way to find out what it is. So for example, that doesn't look like a battery, does it? That's a battery right there. Typically, when you see this, we're talking about like the main. No, just a regular. Like if you were to work on a 2020 Camry or something, that symbol means the battery. That's D12. That's this battery on that normal car. They don't draw it like a Lego-looking battery. They have different symbols. Okay, so there's the battery. For example, here's a capacitor. Here's the actual cigarette lighter. Now, these may vary from manufacturer to manufacturer. That's kind of the annoying part, right? So if you were to hand me off some problem on a BMW or something, I could probably mostly know what the symbols are, but it really may trip me up and be like, what the heck is that? Is that a horn? Is that a video camera? You know, so this is just a sample showing there's different symbols, and then if you can see all the things that are in the circuit, then you can start to understand what could be wrong, right? So you want to do an overall view. So we'll continue on that. Like, for example, here are some circuit breakers, some switches. These are always going to be things that make the circuit do what you want. So power windows. We need to have a source for the power, right? But remember power is volts times amps, so you could call it power. Technically the battery provides both of those. We're going to take the source, probably the battery, and then we're going to send it through something that does work. That's going to be the load. So if it's power windows, that's the power window motor. Cool. The motor will be on the diagram. You'd be like, there's the motor. And if the motor doesn't work, you need to have an overall view of like what else is on the circuit, right? So like just right off the top of my head, I'd say we're probably going to have the battery, some wiring to a fuse box. There's probably going to be a fuse. Sometimes a circuit breaker would be common for Windows. And the reason why is if you were to try to run your window down after an ice storm and it's frozen, that's going to be really hard for the motor to turn, and that motor can pull a lot of amps and it could actually blow the fuse. So if like every time it rains you try to put your window down and it's icy and it blows the fuse, you're going to bring it into the shop, right? So they probably wouldn't use a fuse. They probably actually use like a self-resetting circuit breaker, probably some type of PTC. You'll see we cover those. So if they were to use that type of circuit breaker and you were to try to put the window down and it were to pull too many amps, it would trip the circuit breaker, which breaks the current through the circuit, and the windows won't work. Then maybe a few minutes later, all of a sudden, boom, the windows work, right? No trip to the shop, no diagnosis charge, no technician involved. It's just a better way to design that circuit, right? So there's going to be a circuit breaker somewhere if it's power windows, but if it's, for example, this one goes bad a lot. The power outlet to charge your phone, the cigarette lighter, we used to call it. Now it could still do that, but cars don't really even come with the cigarette lighter element, but they used to. That one, if there's a problem, that's typically fused, and that's a fuse that blows in a lot of cars. Very common, and if it does, you're going to the shop. Or, if you can diagnose it, cool, but that doesn't reset itself. Make sense? So my first thought would be, let me get the diagram. Let me see what components are involved in this system. So circuit breaker, fuse, whatever. If it's power windows, there's going to be a switch. It may be like a small switch, or it may be like the master switch, which has like all the switches for all the doors. It's possible that the switch is no good. If it's a turn signal thing, see, this is the switch for the turn signal. This is actually a multifunction switch. If you look, it does wipers, high beams, turn signal. So, and sometimes on the end it might be like cruise control. So if there's a problem with, let's say in this case, the turn signals, it's possible that it could be this switch. But the way we do our diagnosis, if you remember, we did the strategy-based diagnosis. We don't just say, well, I know your turn signals don't work. There's a turn signal switch. Replace that randomly, parts cannon style, and just see, like, does that fix it? And if you did, you know, this switch could be a couple $100 and labor. So if this switch is an hour or 2 hours in labor at $100+ an hour, plus the switch is a couple $100, that may be a $200, $300, $400 or more guess. You don't do, that's not how we do stuff. That's a no. That's a, if you're DIY and you're like, I'm gonna save some money, I'm gonna do it myself, but I don't have the skills, then fine. You grab parts off the shelf and you parts cannon them into the car. And it's not real uncommon that a DIY person just throwing parts at the car ends up costing more money than bringing it to a professional technician. And we say, oh, we think it's the switch. Look at the wiring diagram. How does the switch fit in? And then if we wanted to test the switch, we could even test this switch by testing the resistance. If you have the turn signal centered, it should be an open inside. If you have the turn signal going left, if you know which two terminals to test, you could measure the resistance through the switch and tell if the contacts are good or bad. That's how we actually diagnose it. So if you could take a measurement and get a number that proves the switch is bad, then you're like, hey, it needs the turn signal switch. That's what's wrong. You're not guessing. You're not wondering. You're going to put the part in, and it's going to be fixed unless it's one of the very rare chances that there's multiple failed parts, which does happen. But if you're doing this type of work, and you're saying like, well, I need to put the switch in first, and then if the switch doesn't fix it, then I got to do this other thing, and if that doesn't fix it, then we'll do the other. That's your clue. You're just guessing. You just totally wildly, you put a blindfold on and you start swinging, hoping to hit the piñata. When you do like the piñata thing, you all know the reference. This isn't piñata. We don't get to like charge people money to play piñata and just replace stuff. Cool, you can. But you're probably going to get a bad review. You may get hauled into court. You know, there's some issues there. Cool, so for example, all these components and more, we'll discuss how they work. You have to know how they work and then how to test them. Here's a nice example for you, a switch. This switch is normally open. So if you were to just follow my logic, and let's just say that I was the meter, I've got my red lead, I've got my black lead. If I wanted to test that switch on resistance, now that you've heard just a bit, what do you think I would do? How could I test that?
Put the red in the front and the back, and the black in the back.
Right here. And what should I get reading on that meter right now?
0.
Not 0, close. OL, exactly. So just making sure you got your stuff straight. Open. See, you know why it's open? Because look at it. It's not contacting. Cool? This is a normally open switch. It should be open right now. However, how would you test to see if the switch is actually working? Yeah, how do we close it? Well, it depends. Like if we are looking at that multifunction switch, how we close the switch in here is if it's the left turn signal switch to close it, you push this down. You're closing the switch. Now it's touching and it should get, you know, like 0.2 or, you know, very low resistance, which equals good continuity. It should have good continuity through the circuit, right? If it's a window switch, same type of an idea. If the window doesn't work in the down position, you could resistance the switch and push down, and it should go from OL, open, to like 0.2 ohms or 0.5 ohms or, you know, some fairly low number. It shouldn't be like 30 ohms. 30 ohms would be like, remember in our circuit from last week, if you have 30 ohms, that's like an unwanted resistance in the circuit. That's going to consume voltage. That's when you might get that slow functioning window motor. And this is true for wipers, power locks, the headlights, anything that we control with a switch. This is one way to test the switch. Cool, so if you look at that again, a normally open switch should be OL with it normal, which means you're not touching it. And then when you actuate it, push down on the window, flip the turn signal, push the push button start, whatever, then it should read 0.2 ohms or so. That would be opposite of a normally closed switch though. If a switch is normally closed, if you roll up to it just sitting there idle, this should be like 0.2 ohms or so, half an ohm, you know, pretty little. But then when you press it, it should open it, because some switches work kind of backwards. An example for this one would be, you guys ever seen in your car the genie light? The genie light, you know, the little red thing, it looks like a lamp. If you rub the lamp and the genie comes out and you get your wishes. That ain't what that light is. Yeah, the low oil pressure light. So when you see the genie lamp, that means like, oh, I'm gonna get a new car. They're just, you gotta pay for that. You know, see what I'm saying? So the genie light comes on, that means you have low oil pressure. That's actually a switch that's normally closed. That switch has a spring and it tries to close the switch. So if you go in the car and you just turn the key on 2 clicks, you'll see the red oil light is on. And you're like, ooh, that's normal because the engine's not running yet. It's normally closed, which illuminates the lamp. When you start it, oil pressure should build up, and picture the oil pressure pushing right here. If the oil pressure builds up enough, it should open the switch, and what should happen to your genie lamp?
Turn on.
It should turn off. So on is like the normal, and off is when the engine is running. You know, so if you had a low oil pressure light, you could actually test that switch just in that way. It's again, diagnosing it is what we're trying to do. So if you can see the diagram, see the components, and be like, oh, there's a switch in there that's normally closed. Let me measure it. Boom, and it's normally closed as low, you know, 0.2 ohms. And then when I start it, it should go to OL. But if it never goes to OL, apparently that switch would be kind of like shorted. It's stuck together. And then you'd be like, here's my measurement. There's my diagnosis. It's a for sure thing. Make sense? That's what we're trying to do. Get a theory, do a measurement, prove that that's what's wrong. Not like, hey, let's replace your oil pressure switch and let's see if, oh, it didn't fix it. Let's change your oil. Oh, it didn't fix it. Okay, you got to rebuild the engine. And it's sort of like, if I knew I was going to have to rebuild the engine, I would have junked the car. I wouldn't have bought an oil pressure switch. I wouldn't have done another oil change. So you took like hundreds of dollars from me, and now you're telling me that I need to rebuild the engine. It's not worth it. See how we could not be providing a good service? If you don't diagnose it, you're committing the customer to putting money into something that wasn't going to fix it, and you definitely don't want to have them putting money into something that 2 days later you tell them they should just junk it. You see what I'm saying? You just wasted their money. Cool, and then we got lots of other things. So switches are the most simple, I think. And then you have relays. And if you notice, you see this symbol right here? Doesn't it kind of look like a switch?
Yeah.
It's like a switch. It's just like a switch. But over here, does anybody know what this one is besides Tim? Close. It looks like a bulb filament, and it is. This is a load in the circuit, but what happens when this gets 12 volts in ground and current flows through, it's going to become magnetic.
Oh.
So check it out. If this was magnetized, look what the relay does. It sucks it over and closes the switch.
Oh.
So if you guys have ever had a relay problem, it's a lot of times, so I'm not going to draw on this. But let me just pretend. If you had some corrosion right here on this relay contactor, it would give you all the symptoms of a bad switch. It's just the switch is inside the relay. Make sense? So we're going to cover relays pretty extensively, but if there's a relay in the circuit, you need to know, because you could do a lot of the diagnosis right here. We'll be sending 12 volts to the top, and we'll be sending ground to the bottom. And if the relay is not being magnetized, it's not going to make it click. But you need to know, is the problem on this leg? Is the problem on this leg? Is the problem on this leg? Is the problem on, right? So there's 4 different directions you can go on a relay. And if you really understand it, you can get right down to business pretty quick. But you got to really understand it. Gregorio, I saw your hand. Hit me.
About the switch, the oil pressure switch.
Yeah.
How about if there's not really enough pressure to open it?
Exactly. So, and that's why I'm saying we really want to diagnose it. So let's say this is your oil pressure switch and you think it's a bad switch, but you go to diagnose it, right? And right now it measures good continuity, and then you start the engine and it still measures good continuity. That means that either the switch is stuck closed, and it could be, but a lot of times there's a mechanical aspect we need to check as well. So if nobody's here to push the switch open, the switch isn't going to open, right? But We don't have little elves and gnomes and little things in there to press it. The actual oil pressure pushes it up. So if your engine's worn out, the oil pressure won't build high enough to open it. That's why we would start with maybe some basic electrical diagnosis and then be like, ooh, this switch is, seems like it could be stuck closed, but I need to verify by checking the oil pressure. Then you call the customer back and you say, hey, your engine has like 2 PSI oil pressure. You don't need an oil pressure switch. This engine is trashed. You need to rebuild this engine. You need to replace this engine, right? So that's a whole... Remember in Unit 1, we kind of described how you need to know electrical to work on all the systems? It's a perfect example. You could know everything there is to know about the pistons and the 4-stroke cycle and you could even be like porting your heads and polishing and cutting your valves and stuff. But if you don't know anything about how electrical works, you can't diagnose a low oil pressure concern. You're kind of like, we'll bring it to somebody else, and that means if you sit down with me and I'm your boss and you say, well, I can do all this work, but I can't do that work. Well, now you just gave me like kind of leverage to say like, well, you're not worth as much money as you think, Whereas if you say, hey, I could do this and I can do the electrical diagnosis, now I'm kind of like, well, shoot, that's pretty valuable to me. You'd be helping me make money. And if I'm an ethical boss, I'm going to help you help me, right? So if you can do more, you can make me more, I should pay you more. Same with the ox. You guys know about the ox? The ox gets yoked up to the mill. It goes around, and it grinds the grain. It grinds lots of grain. But the ox gets a little hungry grinding the grain. So if the ox is a little hungry, you know what you do? You let the ox eat a little bit of the grain. If the ox grinds 100 tons of grain and only eats 100 pounds, that's an amazing deal. So you know what they say, you don't muzzle the ox, right? If you muzzle the ox, you're like, grind 100 tons of grain, but don't even eat one bite. That's not a good boss. See, so what I'm telling you is true if somebody's kind of ethical. So the more you can do, the better you can serve the customer, the more money you're worth to an ethical boss. But if it's not an ethical boss and they try to muzzle the ox, somebody else can pay you. I'm just not in business, so I'm not going to pay you. I don't want to be in business. It's just not really what I'm trying to do. But if you could do all this stuff, you're worth more money. Make sense? Don't go in being saying like, oh, the rent went up, I need more money. I feel for you, but like that, you're going in underhanded at that point. Whereas if you can say, hey, I can not only do all that work, I can also diagnose all these cars, then you kind of give yourself the upper hand. That's what I would do, if you ask my advice. Cool, so we got a normally open relay, a normally closed relay.
Are relays in automotors usually 12 volts, or are they like 5 volts? I mean,
pretty much always 12. I'm not going to say there may not be some abnormal case, but I've never seen a relay other than a 12 volt relay.
Okay, they're all 12 volts.
Yeah. Now, in a hybrid vehicle, we even use something similar to a relay, but it's usually like it's a SMR, a system main relay, or a contactor. And even those, we do 12 volts on this side of the hybrid EV, but on this side, it's actually connecting high voltage. So typically on the control side, if you're picking up my drift, control side's gonna be 12 volts. I never seen one that's different. Go ahead, Ramon.
Like put a relay on, or is there a specific way to put a relay on, or can you put it on any way?
You absolutely have to have it wired correct. So this needs to be, well, technically you could have the 12 volts here or the 12 volts here, but one of these has to be the 12 and one of them has to be the ground, and you control the relay on this side, and then you have the relay control something on like the contactor side. Okay, now I get you. If you're custom wiring, you have to understand the relay, you have to look at the wiring diagram, you gotta wire it right. If you take a relay out and flip it around, a lot of times those relays are made so the opposite legs, like if you look at this would actually be on this corner, and this would be down on this corner, and then this would be on this corner, and this would be down on that corner. Technically, that relay could be flipped backwards. It's the same thing. If it's a relay that would be a problem if it's flipped, they make it so you can't flip it. So like I've seen where these two will face like this direction, and then these two will face like this direction, and you can't flip that relay. That's actually pretty common Japanese stuff. But a lot of the domestic stuff, there's terminals on 4 corners, but they're slotted, so you can't flip it 90. You could only flip it a full 180, in which case it still does the same thing. So it's not a real... The engineers were smart enough to know the mechanic under the hood flipping relays around. We don't want that to mess the car up. We want it to be kind of foolproof.
Are most relays that you encounter single pole, single throw, or are they single pole, double throw?
It's usually single. It's more simple, but once in a while, you'll see as we get more into relays, we'll call them feedback relays, where in the de-energized position, it may be open, but it would be contacting a different circuit right here, and that would be giving feedback to the computer saying, hey, this relay is definitely open. Then when we magnetize, it'll throw this way. So we do some of those too, but this is the most common.
Okay,
It's
so
the most
it's a
simple.
simple 4-terminal.
Simple, super simple. Yep.
It's not 6 or 8 terminals where you're double throw and all this complicated.
Be very rare. Be like really rare. And then if you guys will recall, we talked just a bit about transistors. And so we're going to come back to this in more detail. But if you look, this relay has moving parts. This has to go click, 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 click. This can do similar job of the relay, but it can do it with no clicky, no moving parts, solid state. So electrical, electronics, they could do similar jobs but different. Makes sense? So we'll get a little bit more into the transistors soon. Solenoid, if you notice, it always looks like some sort of a filament or like a bulb element. That's a load in the system. So if we were to have 12 volts coming in and ground going out, what a solenoid does is it magnetizes. So an injector, for example, if you had a fuel injector, they put a spring, right, and there's this little thing they call the pintle, and the pintle is pushed down by the spring, and when it's pushed down, it seals. When we give 12 volts in ground, it magnetizes this coil, which draws the pintle up, and now fuel sprays. But like, how much fuel? We don't want too much fuel, so we pulse it, right? Off, no spray, on spray, off, no spray, on spray, right? That's an example of a solenoid. So a solenoid is kind of like a bulb, except it doesn't make light. It makes a magnetic field, which can open and close something. Make sense?
Just like the relay.
Yeah, kind of, except the relay is pulling a switch correctly. Right, exactly. It's really similar. Imagine putting a rod through the center of this and having it move something mechanical up and down, like the power locks. You ever seen this? Ready? Dunk, 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 dunk. Simply, they could send that lock rod through a solenoid and have the solenoid with 12 volts in ground send up, with switch it, reverse polarity, 12 volts over here and ground over here, down, switch it, switch it, switch it, switch it, switch it. And that's the game you're playing in the back seat. Your parents are like, stop it! And then all of a sudden they stop working. You're like, I broke it. But little did you know, they used a circuit breaker that self-resets, and all of a sudden it's working again. Yeah, the game is back. Okay, I know these things. Cool, and then diodes we'll get into, showing you the diode test. The most common type of diode that you would understand is the LED, so the light emitting diode. If current flows this way, you get light. Oh. And then if current tries to flow this way, you get nothing with a basic diode. And then a capacitor, which is a little similar. It works on inductance, but capacitors can be helpful in a couple ways, but one, to store a little bit of energy. So for example, if you all of a sudden like lost power, or if there was too much of a power draw, the capacitor can supply a small amount of power or current as needed when the system's a little bit low. A really good example for this would be airbags. So if you guys get, heaven forbid, in some crazy accident and you get hit so hard, like one of the accidents I saw in Ortega was gnarly. The battery was out of the car. It was gone. The battery was like, there was pieces and then there was pieces on the road. If there's no battery in the car, you understand, and it gets so hard the engine dies, you know there's no power to that car, right? How are you going to deploy the airbags, which require 12 volts in ground, to like ignite the squib? It's kind of like, we need power even if we lose power. So in the airbag, we'll put capacitors in there in the airbag module, where it's like, if you get hit so hard you lose the battery, no problem, the capacitors are still there enough to deploy the airbags for you and hopefully save your butt. Cool. in that Ortega case, it saved his upper half, but his lower half was pretty rough. I know, because I tried to pull him out. And it was gummy legs. I was like, oh, these bones are not connected no more.
Were you there?
Yes. I didn't see it, but I'm on a motorcycle, right? So when traffic gets slow, I'm like splitting, and then I'm like, oh, here's why the traffic's messed up. Let me see if I can get the dude out. Nope. Okay, so remember we just looked at that diode? Do you see that this is a symbol for the diode? We do use some diodes in the vehicle that are non-LED. This one, for example, we could use as like a clamping diode for the AC compressor. The AC compressor tends to, when the AC compressor clutches in and decouples with the clutch out, it tends to make a voltage spike, and that voltage spike is not real nice to computers, right? So like the computer chips and processing stuff is like, doesn't want to see big amps, and that thing cycling on and off can actually like send a little voltage spike back to the computer. So we put a diode right here, and it says, yeah, send power to the diode, but you know what? When the power tries to come back and burn the computer, it blocks it. Cool, so that's why we may use a diode. In the case that there's a problem with this diode, it's an easy test, and if it tests good, you move on, and if it tests bad, you're like, hey, I found it, it's a diode, I tested it with my meter, take it out, put a new one in, good to go. So again, that's where we're going, how to test these. Here's a sample circuit. 12 volts from the battery, goes through the circuit breaker. It would never really go through a circuit breaker and a fuse, but this is just to show you. The circuit breaker would be like a nicer way to protect the circuit because it self-resets mostly. The ones in like a typical home, they don't. So if you overload the circuit with too many lights or a short or something, the circuit breaker will trip, and you'll go to your breaker box and you'll open the door and you'll be like, oh, there's one. You have to turn it off and then on, and then it's good, right? But in automotive applications, we generally don't do that. We'll use a type of circuit breaker that cools and then self-resets. Those are nice. Or, because this is a little expensive, we'll just go with a basic fuse that costs like a penny, maybe 2 pennies. And that would be probably the go-to by default, unless they see good reason to do a circuit breaker. Then we got a switch, right? So this is circuit protection, circuit breaker and fuse. This is, what would you say this is for the circuit? This does something for the circuit.
Direct it on and off.
Direct is a good way, but there's another word that we're going to use in automotive. Starts with a C. Control, yes. This directs traffic, but we typically call it like control. There's something that's going to control most circuits. If this was the power windows, this controls the window. So ultimately, you can reach down in and be like window up, window down. Makes sense? This is the control part right here. Sometimes the control part is actually a computer doing the work. So if it was, let's say, headlights, old school car, you'd go click, click on the switch. New car, the computer will look at a sensor, and then the computer will be like, oh, it's dark. And the computer will close the switch. Make sense? So this may or may not be a switch you can physically touch, but there will be some form of control on these common circuits that do work, right? Otherwise, the circuit is not within our control, which wouldn't really make a lot of sense. And then there's always a type of a load. So this is a bulb. It could be a solenoid. It could be the coil side of a relay. It could be an LED. It could be a heating element. It could be it could be the motor, remember? So the load always does the work for us. Now we want this to have the resistance because the resistance is kind of what makes it do the work. We don't really want resistance here. We don't want resistance here. We don't want resistance here. Let me rephrase that. If we have 12 volts here, remember, parents got the $12, they hand it down. If you're like, hey, I'm the only child, I'm getting all 12 bucks, but next thing you know, this connection drops a little, this connection drops a little, this drops a little, this drops a little, and the load only gets 9 volts, this is going to be a dim bulb. Makes sense? So said another way, this is where it should drop the full source voltage, minus small losses along the way. We should not be starting with 12.6 and dropping a half a volt here and dropping a volt here and dropping another 2 volts here, that'd be like, that's a problem in the circuit. Question is where? So again, if I think it's the switch, it doesn't, that just means I think it's the switch. Confirm it. We could measure resistance, and resistance is a good measurement, but voltage drop would be better. Remember we discussed like voltage drop is like testing it under load. It's a more thorough test. If I measure here, I got 12.6, 12.6, 12.5, 12.5, 11.1. I'm like, wait a minute. It went from 12.5 to 11.1. It dropped 1.4 volts over the switch. That's too much. We're paying too much of a toll to cross this little toll bridge. We really don't want to pay more than 50 cents. That's what I'm telling you. Half a volt would be like really the limit. Cool. So we could do the measurement and then be like, hey, you're dropping 1.5 volts, or you're dropping, to be honest, if the switch is really bad, it'll drop the full 12 volts right there. And then you get 0 volts at the load, and the load will be inoperative. Makes sense? The bulb won't even come on. Or if it's dropping a smaller voltage, the bulb will be on, but it'll be dim, right? But we can measure that along the way and be like, oh yeah, you got excessive voltage drop in the switch. Or maybe you don't. But if you don't sell the switch. Makes sense? Just the switch is a common failure point, so we pick on that a lot. All right, so when we talk a lot about these, switch is an electrical device used to turn the current on and off. That's that control word. When it's turned off, the switch opens the circuit. It turns it off. It interrupts the flow. No more electrons going through, no more light, no more heat, no more whatever it is that we're trying to get. When it's turned on, switches close the circuit, which allows the current to flow. So in the case of that bulb, that would mean the light lights up. In the case of that solenoid, that would mean something's magnetized and it moves. Right? Many types of different switches, toggle switches, push button switches, specialty. So some of them are like you flip the switch and it's on and it stays on. Other ones, you have to press it. Other ones you have to press and hold. So some are momentary. There's lots of different types of switches. The way we test them is kind of similar. The worst one is like when it's a specialty switch. For example, this multifunction switch, because there's 10 wires going to this one. And if you want to test the left turn signal, you need to find out which 2 wires are for the left turn signal. If you're testing the wires that are for the wipers, you're not testing the correct switch. So this has a bunch of switches inside. These are a little bit more complicated to test because you need to know which terminals that you're on, right? Which wires that you're supposed to be testing. And we get into that next week, the next week, and the week after. We're going to spend like a month on that. Cool. So here, for example, checking available voltage, 12.6 volts. If we wanted to know if this switch was bad, keep the negative right here. Sorry, keep the negative right here where it's supposed to be. 12.6 here, 12.6 here, 12.5, let's say. That's good. 12.5 here, 0.1 here. That would be a good test. Whereas if we had a problem with the switch, we may measure 12.6 here, 12.6 here, 2.3 here, 2.3 here, 0 volts here. We'd say like, hey, you dropped way too many volts on that switch. Your switch is no good. Simple as that. Cool. And so, like we were saying, the complex switches can have all those different terminals. The way that you proceed on those, you really got to get the circuit, the wiring diagram, or the schematic. So you could call it different things. My go-to is wiring diagram. Some people would say schematic. You guys ever heard, let me see the schematics. Schematics is like the whole map of where all the wires go, what's on the circuit, where they come from, where they go, what load is there, so you could whip out the schematic, wire diagram, okay, and be like, oh yeah, I can see the whole circuit, I know what's in there. There's been a couple times where I would make an assumption and be like, yeah, I think I know the circuit, and then I'm going in a direction, I'm like, this doesn't make sense. Let me back up, I'll look at the diagram and be like, oh, I didn't know that was in the circuit. Let me go check that. And that ends up being the problem, right? So you have to know all of what's in the circuit to know all of the possibilities of what's wrong. And then you're going to do, process of elimination. Cool. So they're going to show all that. And then the terminals are often numbered or lettered. All right. So now I'm kind of I'm kind of getting back to, remember we had that multifunction switch that had 10 wires? Now I'm telling you how to know which wires to test. The diagram's not going to say test the green one and the black one. It's going to be like, you look at the diagram and it shows a little number and it'll be like, oh, that says 3. Oh, and that one says 9. So you know you need to put your meter on 3 and 9. You need to be able to look at that connector. You got to have pretty sharp eyes sometimes and find 3 and 9. And then those are your test points. Been very common that people test the wrong points. They understand, you know, how to do the measurements, but they're on the wrong wires. And they get a measurement that makes them believe that it's one problem when it's a totally different problem. This happens a lot. So as we get further into it, I want you to remember the primary thing is the numbering. Don't lean too hard on the color, because I've seen times where it'll be like, oh, black and white. Yeah, that's it. Well, that's one black and white. Are you sure you're on the right black and white? Because on some of these bigger components, there may be 5 black and white wires. So you're much better off looking at the number or letter. It's probably going to be mostly number. And then you can double check yourself by confirming the color is the same. And once in a while, the color is not the same, and you're like, is it an error? Did someone else work on it? Did they write the wiring diagram wrong? Or I've even had other times where I'm working on some car with a 4-cylinder in it, but I've accidentally pulled the diagram for a 6-cylinder. And so I think I'm on the right wires, and the colors don't match up, and I'm like, I'm doing something wrong, but I'm very invested in the problem, and I'll say like, let me just walk away. You know what I'm gonna do? I'm gonna go get a nice breakfast burrito, some horchata, and then I'll come back feeling good, and I'll be like, oh, this wiring diagram is for the 6-cylinder, and I got a 4-cylinder. Dope. And then all of a sudden when I get the right wiring diagram, things are making sense and I'm back on track. But sometimes walking away is how you get them. It's electrical can you'll be like so immersed, you're just like a dog on a bone. You're like, I'm gonna get it, and you might be going digging the wrong hole. You're supposed to be digging over there. Cool, so that happens a lot. Sadly, at least for me. Okay, here's this switch. Boom, the multifunction. Here's how that fits into the diagram. Let me see if I can zoom in. I don't know if I can. No, I can't zoom. But just to give you a general overall view, like there's a whole bunch of switches. I'm going to count them. 1, 2, 3, 4, 5, 6, 7, 8 switches, 9 switches. So, and these are a little bit different. So we got the fuse box right here. That's where the source gets protected, right? So this probably comes from the battery, goes through the fuses, goes to the switch in one spot, goes through to the switch in another spot, goes to the switch in another spot. This one's for headlights, this one's turn, and this one's hazard, you know, the 4-way, the flashers. If you pull over and you put both left and right on, those are the flashers. So if you have, yeah, that's your, I want to race you indication. So if you have a problem on the headlight, you know, the headlights don't work, I don't want you over here probing and testing stuff to do with the hazard and the turn too. You really need to be right here, partner. So there will be letters, there will be numbers, I should say, right? So if we're trying to test that switch, we need to know which wires. If you're testing this wire and this wire, that ain't testing the headlights. Make sense? You got to know which ones. Then, like I said, technically you could just do resistance from A to B. That'd be okay. But better if you test it under load and you could see how many volts it's dropping. So if you put this on the ground and you said like, okay, 12 volts in, 0 volts out. What's that tell us? 12 volts in, 0 volts out. It's dropping all of it in there. So that means we have like an open circuit inside. Should we have an open circuit inside? Unless you forgot to turn the headlight switch on when you were testing it. And then you're like, oh yeah, if you want to actually test it, you got to turn it on. And let's just say now you test it, you got 12 volts coming in, you got 12 volts coming out. What's that tell you about the switch? Switch is good, yeah. Makes sense, so just keeping in mind, this is a normally off switch, so you gotta turn it on to actually do the test for voltage drop, or available voltage. Cool, right? And then you can see here, this one's another one that's another type of combination switch, but this one is actually doing relay control. So this would be pretty common. If we were to look at this one, let's say these are the headlights and taillight switches right here. So we got terminal 1 needs to go through the switch, and if it's an off, it dies right there. It doesn't go any further. And if we move it to tail light or headlight, that should connect number 1 to follow it. You ready? We're going to follow it. I'm going to do this. I'm not going to mess this up. I'm moving this up. Don't judge me. All right? If we were to trace it, which is one of the things we're going to be doing pretty soon, I'm going to help you out a little bit on this. We should have 12 volts coming in, and then the 12 volts should go to the load, and then in theory, we should actually have this drop the load, because see, can you tell that's the load, the coil? So we should actually drop to ground right here. Should go to here, the ground should go to here. If we're testing it with the tail light on, this should swing over, right? So we can just draw that in. Boom, boom, it goes down. And then look, it goes to ground right there. So if you understood this diagram, you'd be like, oh, okay. I should have ground on terminal 1, and I should have ground on terminal 7, if this switch is good. If I want to do it with resistance, how would I do that? Anybody know? I put this on 1, I put this on 7, and if I turn the taillights or headlights on, how much resistance should I have through the switch?
0.
Yeah, like good. It should be like 0.2, like basically good continuity. If you didn't understand that, don't worry. This is what we're going to be doing for like a couple weeks. Okay, so that's fine. But if you kind of understood, we take a measurement on 1 and 7 because we don't really care about over here. I don't want to test all those. That just takes too much time. Why would I do that? They didn't say they have a problem with these circuits. Leave them alone. Test this one, but see, you can't break the switch open and test. You guess you could. You could go and be like, rip the switch apart and be like, is it good? Is it bad? You know, that switch isn't going back in. Makes sense? That'd be crazy. That's like what an animal would do. Okay, so you're not going to rip the switch open. You're going to find terminal 1. You're going to find terminal 7. You could do all the diagnosis you need to do on those 2 terminals. Yeah, kind of. If you don't totally understand how to test it, that's fine. But you got to at least understand what I'm saying, how we test that switch inside of the big switch. What you think? What you think, Ramon? You like it?
So the top 3, they're not related?
They are, yeah. Okay, now I'll give you a little bit more, okay, without totally overloading you. If you're good old flat rado, this is how I would test the switch. I'd turn the switch on and off, and I'd see if the relay clicks. If the relay clicks, it tells me everything I needed to know. If the relay clicks, that means it got 12 volts here. So the fuse is good, the connector's good, the relay's working at least in that way. And then it would need ground down here to activate this load. And if it activates the load, remember, what's the relay do right here?
Energizes.
Yeah,
Magnetize.
bingo. And when it magnetizes, you know what it does? It makes this little contactor come over and click. So if I hear the click, I don't really need to do another measurement. I know that it's got 12 volts in ground right here. So like the switch is good, I'm moving on. See, so if somebody really knows their stuff and you're like, oh yeah, I can do that. Like you just do some stuff, and if there's some clicks, and you just replace some stuff. Like you walk outside and you see the eagle flying. Have you seen it? You look at the eagle way up there, 300, 400, 500 feet out, and there it is. And you're like, I could do that. Look at it. It just does this. Well, I'm gonna take you up there. I'm gonna shove you out the plane and watch you be like this. You know, so if you see somebody who knows, they make it seem like this is easy and simple, but it's not. See, what you didn't see is all the years the eagle spent learning the air, fine-tuning the muscles, learning how to ride, plus it has wings, so that does help too. But if you see somebody do electrical diagnosis and they make it look easy, it ain't. It's just because they really know their stuff. Make sense? I don't know. You'll have to judge me. We'll see. What if sometimes I crash land once in a while though. And you'd be like, man, that eagle's got something wrong with it. That eagle needs rehabilitation. But if you're all really gonna do this, you're gonna end up working with people on the job. And like, if you see somebody make it look easy, that's the person you wanna be like, hey, let me work with you. Like, show me the way, you know? You know the way? You need to know the way. You need to be shown the way. That's how you do it. All right, cool. Then this is what's also kind of nice. This is the connector end view. So we wanted to test 1 and 7, right?
That's the relays usually have that on the back of them, right?
They do. They put terminal numbers, yeah. If we wanted to test this switch and we knew it was 1 and 7 based on the diagram, because we're only concerned about the headlight, tail light switch, you'd be like, oh, 1 and 7, where are they? You could find the connector end view, and this would say top left corner, lower right corner. So you kind of go together with these.
I get it now. I was a bit confused, so that's what the numbers are. Okay.
Exactly. So this is telling you what they are. Now, they might say that this is red and this is black, but I don't recommend really primarily going after that. I'd be like, primarily you want 1 and 7, get the connector end view 1 and 7, and then double check yourself. Be like, red and black. Yeah, it's not only 1 and 7, but this one's red and this one's black. Like, I know I'm on the right wires. And then you can make just one test, maybe 2 tests, and be like, it's diagnosed. Cool? Whereas if you don't really know, you're like, let me take this out and substitute this part in and go down to AutoZone and plug a thing in and then get a different thing. And like, you know, you can figure it out just by shotgunning parts in, but then why are you here, right? Okay, and so we talk a little more about fuse and circuit breakers. Just to remember, just to remind, the fuse, the circuit breaker, fusible link is something we're about to introduce. They have one job. Protect the circuit. Mostly the wiring. Protect the circuit. So if there's too many amps going through that circuit, we want the fuse to poof. And then we can take it out and put another fuse in, and that fuse goes poof, and you do it one more time, poof, just to make sure the fuses aren't defective. And then you're like, let me put a bigger fuse in, right? No, now you no longer have the protection on the circuit. So if the fuse is blowing, you need to diagnose the circuit. Why is the fuse blowing? And you should be able to figure out why. Cool, so, and then similar, when we talk about this PTC, positive temperature coefficient, here's what that means. When something gets hotter, the resistance, it's a positive temperature coefficient, so the resistance goes up. So if the circuit's chilling, the resistance is down, current flows right straight through the PTC circuit breaker. If we get too much current flow, it gets hot, right? And if it gets hot and it has a positive temperature coefficient, that means the hotter it gets, the more resistance it gets. So what starts happening to that circuit?
But less electricity goes through.
Yeah, exactly. And generally, it'll get to the point where pretty much this thing becomes like OL and it's like open. Cool. And then because it got hot, right? And then it opened it, but then what happens when it cools off?
So the hotter what gets?
When it's a PTC, this is a specific type of material. The hotter it gets, the more resistance it gets, so it protects the circuit.
The hotter the fuse gets?
Well, this is not exactly a fuse. It's a PTC circuit breaker.
Oh, okay.
So fuses, they get hot and they melt and they go poof. But a PTC circuit breaker gets hot and it's like, makes a bunch of resistance. And then once it cools down, what do you think happens? Right back to normal. That's why we like to use those in the power windows, right? Because your windows freeze up, you can't get it to work, you can't get it to work, you can't get it to work. You might actually overheat the circuit, but no problem, because the PTC circuit breaker will add a bunch of resistance, protect the circuit for you, and then once it's cooled down, the actual circuit breaker itself cools down, boom, all of a sudden the windows work, and hopefully by then you got the windows defrosted and they can move.
That turn off.
Exactly.
Okay,
on and off themselves.
Like reset themselves.
Yes. So if you want to remember it like this, the PTC circuit breaker is really just a self-resetting breaker. It'll protect it, it'll reset itself. Really nice, but some of these are not accessible. Sometimes they'll put them like in the motor. And so if they go bad, you can't like replace them. You have to replace the component, you know. So that's a little bit of a pain. That does happen sometimes. And then remember, fuses and circuit breakers are rated in amps. So, and amps, they're rated by their wire size. So if you have wires that's a wire that's good for 20 amps, like let's say a 12 gauge wire that's good for 20 amps, that means at most you're going to put a 20 amp fuse in there. Technically, if you wanted, you could put a 15, but you know, you don't really need to. The wire can handle at least 20, so it's good to run a 20. That's probably the way it would be designed. Remember we talked about last week, you don't you don't want to run a big wire if you don't have to. So if it's a circuit that's only going to pull 15, you could run a 14 gauge. If it's going to pull 20, you'd run a 12, but the 12 is more money than the 14. So we're going to save some money there. Cool. But that's why we can't be increasing the circuit breaker or the fuse size. Cool. So here's like several different types. These are your original. These are just called like blade type fuses. Then new cars have more and more electronics, right? So these are too big. They're like, hey, we need more space. So they did the mini fuses. And they actually have fuses like this that are low profile. And then they have fuses like this that are even minier. So they call those the micro fuses. And then we also have these glass fuses. This is old school. You would generally not see this in a car unless it's like an old car. And this is the one where if it blew, you took this out and you put a little 22 caliber little ammunition in there, and there's all these rumors about, oh, I had a short, so I put a little 22 bullet in there and it shot me through the leg. I'm like, nah, I don't think that ever happened. That didn't happen. Okay, but it's still a fun story. So especially like, if it's someone like West Virginia, and all that. These are the stories. These are the stories. Okay, or it's aftermarket. So if you buy cheap aftermarket, like maybe like some fog lights or something, they may put one of these glass fuses in. These are hard to find. This is a real hassle. I'd cut that piece of crap right out of there and put a regular fuse in because I'm not carrying a bunch of those. Then we got some Pacific style fuses. A lot of these tend to be a little bigger. A maxi fuse, so you can see like this is a blue, I think it's a 15 amp. Over here you got like a 60 amp.
Those ones are so horrible. Like the one with the 50.
Uh-huh.
Those ones like when you're trying to remove them,
they're hard to get out.
They break so
Yeah.
easy.
Yeah, they're hard to get out too. So yeah, there's lots of types. You'll find them in the fuse box. So here we got quite a few fuses, quite a few relays. You guys should all know on the underside of the fuse box or sometimes on the top, it tells you what size fuse it should have. You don't be putting bigger fuses in there.
When you said the hotter that it gets, the more resistance?
Correct.
Okay, I was just...
Yeah.
Paul,
For PTC.
Where would be a good place to buy a collection of fuses, for home repair?
Okay.
for cars? I
Good.
mean,
It's a good question. You can get them on Amazon. You can get them at Harbor Freight. If you wanted like just, if you just want to be prepared for when a fuse blows, you can buy an assortment. You can get all sorts of different mini fuses. But then you're like, am I going with like full-size fuses? Am I going with mini fuses? Am I going with micro fuses? So it tends to be, there's so many varieties now that it's kind of a pain. The thing that I like to do, if a car, let's say you went to the junkyard or a car was going to the junkyard, I'm taking the fuses.
Oh.
All of them. I'm gonna take them all. So my toolbox right here, lower left drawer, one up from the bottom, I open it up and I got all sorts of random fuses and stuff.
Yeah, relays and fuses are expensive now.
So that's kind of why I like to, if something's getting trashed, I'm just gonna grab, because it's quick, right? I'm just gonna grab boom, 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 boom. So back in the day, I had quite a few fuse boxes that failed, especially when I was in the Northeast. It's rusty and salty and there's corrosion. If you get corrosion inside, you can't really fix this. So be like, yeah, the fuse box is bad. Sell the fuse box and then take the old fuse box and throw it out? I don't think so. In the toolbox and then throw it out. Customers don't want them. So I got my own assortment just from, years of being cheap. I'm gonna say cheap. That way I'm putting myself down.
That's smart.
No, I'd say cheap, but it is kind of smart though too. Right? Now, what I'm not saying to do is when you're in Walmart and you see somebody's got the hood pop, go over and start yanking them. This is cheap stuff. This is not something that's worth stealing. But if it's something that's going to the junkyard, I'd get them. For sure.
Are these relays and fuses pretty standard? I mean,
Yes and no. So if you look, this, the same. These actually look like they may be different. If they're going to be different, a lot of times what they'll do, they'll put a different color, a different number, and sometimes they'll change the orientation of the terminals. So like one really good example, the horn, the headlights, all that stuff is like a fuse that's good for like maybe 15 or 20 amps. But then the fuel pump, maybe like 25. They'll make a different relay because it's doing more work running a fuel pump than for the headlights. But you wouldn't be able to, hopefully you wouldn't be able to interchange them. And if you do, you're kind of messing up.
I've always had how do you check those gray ones?
I'm gonna show you
Okay.
soon. I think
Those
it's
are relays. Those are considered
exactly,
relays.
yeah. And if you can test a relay, you can fix a lot of stuff. So even professional technicians that I've worked with, you know, their way of testing a relay, and I can't blame them, okay, because flat rate, you guys understand, you get paid for the amount of jobs you produce. So the faster you can diagnose, the more profitable you are. Their go-to is, I take this one out, I take this one out, I switch them. If that is all you need to do to diagnose it, there's nothing wrong with that. There's one potential problem. If this one was bad and now it's there, but you forgot where it went, you're like, oh yeah, the horn wouldn't work, and then I switched the relay and now it works. Like, where'd the bad relay go? I'm not sure. Well, now something else isn't gonna work, but you know, so that was a little dumb. But there is a way to actually really test these, and I'll show you how. Because once in a while you get like, this one is, well, maybe these two are the same. But if you get one that's a standalone that you can't do a quick swap-a-rooney, you do need to know how to really test them.
So as far as these relays are concerned, I mean, across different makes.
Yeah.
Let's say a Honda, Toyota. Or
I got you now.
Right? I mean, do they have the same form factor, the same specs typically, or are they like, okay, this is a Toyota, it has to be a Toyota set of relays?
I got the question. Let's say you're working on a GM.
Right.
The GM's going to be the GM's going to be the GM, but probably GM didn't make them. Probably Delphi made them.
Yeah.
So if Ford also hires Delphi, they're going to be identical. Typically, the Japanese companies seem to be using the same relay manufacturer as the other Japanese things. But if you pop the hood on a Japanese car, it's probably going to be different than a Ford, you know, for sure. So there is some variations, but especially like, let's say it's a Honda, the cooling system, the cooling fan relays go bad a lot. This Honda to this Honda to this Honda to this Honda, they're going to be probably the same, unless it's like a 1990 Honda. It's like a 2020 Honda, they might be different. And here's the other justification why you need to really be able to test these and not replace them. These relays take up a lot of space, would you agree? The cars have a lot of electronics, we're running out of space. You know what they do? Eliminate the relay and do an internal, non-serviceable, non-removable relay. You can't swap it. So if the relay is built into the fuse box, whether a transistor or an actual traditional relay, you have to be able to test it. You can't take it out and put it in. The only way to do a swap would be to swap the whole fuse box, and that's like a big job. So you have to know how to test these, because these easy serviceable ones are less and less and less, unfortunately. Sadly. Kind of sadly. So more symbols. A regular fuse, a medium current fuse, so that's more like this different style. A high current fuse, which could also be a maxi fuse, different style. And then sometimes they'll call it like a fuse, an M fuse, an H fuse. A fusible link is something that I need to make sure you understand. A fusible link doesn't look like a fuse at all. There's nothing that you can remove and reinstall. It's actually a section of wire, and this little section will be smaller than the rest. So if you're running a 14 gauge wire and you want, actually let's make it a 12. If you're running a circuit where 12 gauge is like most of the wire, and then you put in a little smaller 14 somewhere, where would the failure occur? Exactly, but they'll put it like it'll be like a little bit more gummy insulation, thicker insulation. It's something where it's designed where this will melt and it'll turn kind of gummy. So it sounds crazy, but the main way we used to test fusible links, you go grab it on two ends and you'd pull it. And if the wire was burned inside, it would stretch the insulation like a balloon or like a rubber band. It'd be like boing, and you'd be like, oh, okay, got you. The other thing you could do is you could measure it with your meter, resistance, or check the voltage drop. If your voltage going in is 12 and your voltage coming out is 0, you already know the fusible link is shot. And then when you go to fix them, sometimes you have to replace the harness, and other times you can actually splice them in. The good news is these are kind of less now. They're not doing all that much of those. They used to do it more back in the day. And then here's a circuit breaker, and you can see that appears to be a self-resetting because there's no button or switch, or there's no mechanism for you to reset it. And then remember, typically circuits are protected by a single fuse. They're designed so that normal current does not exceed 70%. So we shouldn't really be blowing a fuse. If you're blowing a fuse, you're over the 70%, there's something wrong. So putting another fuse in is just like a Band-Aid. Like it's not solving the root cause of the issue. Makes sense? So if it blows the fuse, do the diagnosis, which we could talk about a little bit more. Excessive current draw is something there's a lot of different ways to figure it out. Some are a little more thorough and some are a little more easy. So there's the blade fuse, mini, low profile, maxi. Colors, it's not real critical, but just so you understand, things are color coded. So if you need a blue fuse, that's a, okay. So if you need, let's see, I said that wrong. I was gonna say, if you need a 15 amp, what color would the fuse be? Oh, I blew it. All right, how about this? If you blew a red, my goodness. If you blow a 5 amp fuse, what color are you looking for?
10.
There you go, right? So when you open the drawer up, you don't have to be like, let me read the numbers. You just look for the color. Makes sense. So the color is going to be standard. And then same with the maxi fuses. So the 30 amp green one, it's kind of interesting. You could have a mini or a standard fuse that's a 30, but sometimes you'll have like a 20 or a 30 that's a maxi. I don't totally understand why they do that, but just so you know, these are generally bigger, but sometimes not. It's kind of funny. Cool. And then this is called an ampacity chart. And I just want to skim it just so you can make sure you absolutely understand what I'm saying about switching fuses. So let's just say I have, and this is under 50 volts with potentially 105 degree insulation that's good for 105 degrees. If I have a circuit that needs to be able to pull, let's go with 35 amps, and it's outside it's like just outside, it's a body harness. It's not in the engine compartment where it gets hot. If I need to pull 35 amps, what size wire should I use? Okay, how'd you figure that out? You found the ampacity. If it's just a body harness, not an engine space, and you're like, oh, 35, here's how many ohms it has for every 1,000 feet. Here is the actual area, the space. Number 14. So 14 would be the gauge size. If you needed to pull 45, what would you go to? 12. So do you see, this is smaller and it's getting bigger. If you needed a battery cable that could do, let's go with, how about 300 amps, what would you do? 300 amps. The option would be, if it's 0, that can do 285, so that's not enough. We have to round up. Yeah, so 2 watt, so that's going to be like a, that's going to be a big sucker. That's battery cable. So when you see the battery cables, there's a reason that the battery cables are that size. The battery cables are sized to be able to pull all the power out of the battery, send it to the fuse box, send it to the starter, have some stuff coming back from the alternator, right? So they size all these wires based on, they do their calculations. They know how many watts, they know how many amps, they know all this stuff, and they figure out what size wire it should have. So if you were to have, it'd be unlikely to have these be fused, by the way, but some of the ways that they'll fuse them was a fusible link. Other ways that they may fuse them was they can run through like a big bus fuse that's actually bolted in. So if it's going to be 400 amps, that's not going to be a fuse you pull in and out like that. That's going to be a fuse that's like got a terminal that's bolted down to a stud, got a fuse that's bolted down, and got another terminal that's bolted down. So it's a fuse, I guess I should reword. It's fused, but it's not like fused. See what I'm saying? Yeah, like a mega or a mega fuse. That'd be pretty common, the ones that are bolted in. So I'm gonna hope that we don't experience this, but like if a customer, it would never be us. We never make mistakes like this. Jumps their car backwards, it'll potentially blow the mega fuse. That's the main power fuse right there. You don't just pull that out and put it in, and that's gonna be something that needs to be unbolted. When it's really high current and potentially high heat and stuff, we actually bolt them so they're tight. So that way you don't have like a little looseness and arcing and sparking, because that could actually make too much heat melt plastic, potentially cause a fire. So if you get into this big stuff, that's a, you know, it's not a quick pull the fuse out and put a new fuse in type of thing. Cool, so that should give you a general, pretty good overview. So if you had that 14 gauge wire, that's good to up to 35 amps. If you were to put a 45 amp fuse in there, that would mean that the wire will burn before the fuse, and that's how cars catch on fire, okay? That does happen. Not after you graduate this class, it don't. Cool, and then circuit breakers, just talks a little bit about how they work. A bimetallic strip heats up and bends, which means it's open. That's why if you look at the diagram, it looked like a couple different wires. It's actually two pieces of metal, and when they get hot, they kind of like pull apart from each other, and it physically makes an open, and then it won't work anymore. And then sometimes we need to reset it, or other times they cool, and now it'll start working again, unless it gets too hot, and then it'll open again. They can fail, by the way, but not super common. Cool. All right, and then here is a good shot of that fusible link. Red wire, red wire, red wire, and then it's kind of into this weird like black gummy looking thing. If this fusible link was bad and you were to grab an end and it were gummy, you'd already know that fusible link's no good. You could also cut right here, but if it wasn't good, you just cut it in half. So you really already need to know that it's bad when you cut it or measure it. The negative of measuring is we don't want to poke the insulation because now you just ruined its waterproof characteristic, and now it's going to be corroded, whether this year or next year, some year, be corroded. So these can be a little tough to test. Sometimes you got to test way over here and then way over there, but usually that's why I tug on them. Cool. And then the circuit breakers with the bimetallic strip, you can see. This one's cool. When this one gets hot, look, it's like this. It's open. When it gets cool, you know what it does? Closes and they contact again. So that's the visual on the circuit breaker. Cool. And then we talked quite a bit about the PTC, Priscilla's favorite. This is what we were saying. So they have a very low resistance at room temperature. So that means current will flow right through, no big deal. But if too much current starts to flow, the current flow increases the heat, which causes the resistance of the PTC to increase. Make sense? So now it has more resistance. If it has more resistance, that means it's going to drop more voltage, and that should cool the system down and also protect the wires, you know, because we're worried about the wires getting too hot. Adding resistance lowers the temperature, which cools the wires, which keeps us safe and not on fire. Cool, so these are pretty good. And then look, PTC's general reset once power is removed and they are cool. So if it was the power locks, chunk, 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 and it messes up and you're like, oh no, just chill for a bit, and then all of a sudden they'll come back. That was kind of the lesson. Cool. It didn't ruin the video, did it?
No, I was making sure.
Good, cool. Yeah, just ignore them. Okay, remember we were talking about those big maxi fuses and stuff? Sometimes they can look like this too. These are my least favorite because these ones bolt in this way. So if you're looking down, you got to take all sorts of stuff apart and undo like a bolt or a screw or a nut and a stud or something, unbolted here and unbolted here. The reason they've gone to this, those maxi fuses that Gregorio was describing, you'd look straight down at them and there'd be like a stud and you could just unbolt them, and it was nice. But they take too much space. So when they're like, hey, we need a big maxi fuse style, like a mega fuse for the alternator, the battery cable, the other big thing, like especially if it's something that, let's say, has the inverter for the power outlet in the bed of the truck, so you can do your power tools, you know. So they used to be one. Now they'll be like, hey, we need 4 or 5, 6 of these big circuits protected. We don't have room for all those mega fuses, so they'll put them in one. So this will have a fuse here, 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 but it's bolted in. You got to disassemble the whole fuse box to get that. Oh yeah. Mason, you seen these?
How would you test those if you had to? Like...
Good question. Okay, the honest answer is, if you get your flashlight down here, you can look and you can see if it's blown. That's the real simple answer. The way that you could do it with your meter is you could test, the big battery, the positive terminal, to whatever the circuit is. But a lot of times the test points are inside the fuse box, so we don't usually do that. You get down in there and you look and you'll see from the side if they're blown, but you can't pull them out and look at them. So they are kind of a hassle. We could check them out. We have them on a couple vehicles out there. Cool, and you can see there's actually 2 of them on that one. So kind of a pain. Right now we're going to talk about flashers, and we're going to make the flasher discussion slightly abbreviated, mainly because we don't really do it like this anymore. However, old cars did, and unfortunately it's still kind of on the ASE and stuff, so you want to at least understand it. When you say flasher, that means you put the turn signal on, right? And what happens? But are you in the seat doing this with the turn signal? If you are, it's broken. I'm just letting you know, so you can have that fixed. All right, so the flasher is what makes it go illuminated, not illuminated, illuminated, not illuminated. Okay, old car, you get in that turning lane, you're trying to go left into Costco, you're like, oh, this is taking forever. I really want the pizza combo deal or whatever. You remember the noise it makes? That was literally the flasher. The flasher actually made that sound. People got used to that, and that would be the reminder their turn signal's on. New cars, we got rid of the flasher and we do it with the computer, and people would forget their turn signal, so they actually started making it so the computer sends a signal and it'll actually add a little speaker so it'll make the sound. We don't need the speaker. The only reason the speaker's there is to help people feel like it's still the way it used to be so they don't forget it's on. Make sense? If you really want to be technical, you could eliminate the speaker, or you could put a speaker in and be like, hey, your turn signal's on. You could program it to say that. Hey, your turn signal's on. Wake up, ding dong. You could come up with your own custom types of things. So they no longer use this, but everything we're going to describe is going to be the old school way of doing it. So they used to look like this. So you'd say power and away would go in and come out, and this would on its own contact and then not contact and then contact and then not contact. Cool. Then they went to more like a little bit of a relay style, and a lot of times these have become more electronic. So this was purely mechanical, bimetallic strip, heat up, separate, cool down, contact, heat up, separate, cool down. These can still make noise depending on the style, but in a new one, actually both of these are gone. And they'll just send it into the control module and it'll come out flashing. And the transistors, whatever, does it on its own. So there's some more circuit breakers too. Here is, okay, electronic flasher. I'm going to sell you on why this is kind of better. On the old school flasher, you had to have the exact right amount of resistance on your turn signals front and rear. So who's ever had a turn signal bulb not work? How do you know?
Because it wasn't blinking.
All right, that's one way. How could you know without even getting out the car?
Oh, if it's not showing on your head.
Oh yeah, you've heard them where they go fast? That was because when that bulb was open, and by the way, it could be the bulb, it could be the wire, it could be the connector. When there's an open circuit in that system, the flasher heats and cools faster, and it goes tick, 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 and you'd be like, hey, I think I got a bulb out. You don't know if it's front or rear, then you got to get out the car. I agree with you. But the old school was because you lost that turn signal bulb, it would make the flasher turn faster. The new school, so I guess here's the negative of that. If you wanted to go to LEDs or you wanted to add other turn signals, that would all affect the overall circuit resistance, right? Because they'd be in parallel. Remember, when we add parallel circuits, it lowers the overall resistance. If you added some bulbs or if you put in LEDs or whatever, you're affecting the resistance. That flasher is not going to flash. They might do solid. It might flash super fast. So you'd have to find a flasher that matched your resistance and whatever. So it was always a hassle, especially with the new cars having LEDs from the factory. These old school flashers don't work real well. So we've gone to electronic. The electronic flasher doesn't really care what your resistance is. It just knows, I go on for this much time, I go off for that much time. I go on for this much time, I go off for that much time. So on these systems, they could flash normally even though you have a bulb out. But what do you think the engineers noticed? People didn't get the fast flash, so they didn't know that it was out. So they've transitioned back to like, hey, if there's a bulb out, we're going to monitor the circuit using the computer. And if there's a bulb out, we'll program the computer to make it flash fast artificially, just so it prompts them to get their turn signal light repaired. Kind of crazy, huh? So that's what they did. So on a new one, if it flashes fast, that's the computer basically doing it manually because it knows you got a bulb out because it's monitoring your current flow. It could do that. Cool. So it's still a giveaway. Which is nice because now we do LEDs and you do all sorts of crazy stuff, and it could always flash the same if it's the correct resistance it was designed for. Oh, and then also there was the turn signal and there was the hazard. So a lot of times there was a hazard flasher and a turn signal flasher, and they were separate. But then on the new stuff, because it's electronic, we just have a computer that can do both. So there was this weird transition period where there was 2 flashers and they were old school mechanical. Then there was 1 electronic flasher. It would have the turn signal and the hazards going into it. Now we'll just send both of those to the body control modules and figure it out. Body control module makes everything happen. Exactly how? Well, that's a little more complex. All right, so here we are with relays. So I'm gonna say I'll skim just a bit. Remember, the relay has the switch. That's going to make the contact or not make the contact. That's an important part. But we also have what's called the coil. This is the coil. So look at that coil and look at that switch. Now let me back up just a few slides. Right here. I want you to picture this, but I also want you to reference the other one. Remember that coil, right? That's how it looks like. But then on the wiring diagram, this is how it looks. So now can you see how this is the coil? It kind of looks like a coil, right? And then can you see the switch? This one has feedback, for example. So the switch is going to open and close. Get in detail on that. Okay, so if we're right here, what I want you to understand is 85 and 86 are what we call the control side of the relay, because they control the relay. Right? 85 and 86 are going to be small wires. And you can remember these numbers or not. Truth be told, I don't remember the numbers. So if you're like, oh yeah, I got a problem on the 85 circuit of the relay, I'll be like, right. Is that the control side? Yeah, it's the control side. Cool, now I got you. So you can memorize it if you want. My memory is I'm just not good at that. I comprehend it. So if I know I've got a problem on the control side of the relay, the 85 and the 86, those are small wires, itty bitty little wires. So let's just say, in this case, we got B+, that's 12 volts, 12.6 probably, coming down, going to 86. If 86 has 12 volts, how would we make this coil have current flow and therefore magnetized? Tim, don't you answer this. How would we make this magnetized? What would we have to give it? It has 12 volts. Hey, I heard that. It has 12 volts, right? 12.6 it has right here. It won't flow until we close this switch and therefore supply 85 with ground. Now can you see the circuit? Right? So if I were to not draw on the thing, I could trace this again. In fact, I might even switch out for an orange. Let me see if this orange one's better. All right, we got B+ right here. See that? And it goes right to here. Now, if that coil functions correctly, it should drop it and go to ground, which should go through the switch because we're closing the switch now, right? Boom. If that's what we have, that sucker's magnetized. If that sucker's magnetized, what's it going to do for this sucker here? Click. Okay, so now let's draw it in closed. And now you'll kind of see what's happening. Look what also happened on 30. 30 pulled off of the 12 volt positive, and we had 12 volts going to here, and it was dying right there when it was open, but now that it's closed, what happens?
87.
Yeah, it continues, continues, and it goes out 87. And what do you want to do down here? I don't know. How about we make a bulb? Light bulb. We'll send that bulb to ground. Do you see how that relay just controlled that bulb? Kind of, sort of, a little bit. That's what the relay does. But wouldn't you say we could eliminate all that and just have this switch right here and just send we could send B plus in and just have it go through the switch and then turn the bulb on or off? What the heck we need the relay for? So now I'm going to help you understand. If this was your headlights are probably going to pull 10, maybe 15 amps. Sometimes, like with some of the bigger old school ones, and sometimes when we get into some of the really powerful HIDs, and sometimes we have multiple headlights and stuff, it could be more. This is the thing. This switch, remember we closed this switch right here? If that switch was your headlight switch, the more amps it flows, the stronger it's got to be. It's got to be like your headlight switch isn't going to be one of these. It's going to be like a. You want a big type of switch? You want some big heavy duty type of switch? You can't. You have a new car. A new car's got all these little dainty, nice switches. You got a multifunction switch. That switch is tiny. It's got tiny switches inside. If you have a tiny little bridge, you think it's going to be able to handle that many cars? The cars are the electrons, remember? You think that tiny little bridge is made for thousands of cars to go across it? No. So here's what we do. I'll even draw the basic circuit right here. We'll do a B plus coming down, send it through the bulb. We'll make the switch right there. We'll go to ground. You guys can see the switch. So if you wanted to make the bulb glow, you just close the switch, right? But if there's going to be 15 amps going through here, that switch has got to be big boy. The switch has got to be hefty. The switch has got to be made to handle a lot of current. Now you can't have your little tiny multifunction switch. You can't do that. I can't do that. So this means strong switch. So instead, here's what we'll do. Remember we had a little switch. Where was our switch? On the control side, you guys remember this switch? These wires are tiny. This is low current flow. We can use a little itty bitty little switch right there. That could be the little multifunction one. You see what I'm saying? So if we use a little itty bitty switch, cool, and these little itty bitty wires, maybe we make these wires like a 24 AWG. Cool, smaller wires, smaller switches, but what's it actually do for us? If we close this, it magnetizes the coil, which closes this up here. This is a big switch. So this one can handle the 20 amps or more, right? This one down here, this one, we only really want that to handle 5 amps, cool? The relay, worded in another way, is a way we can use little amps to control big amps. Make sense? It's a relay. It's like hey, if we can open and close this tiny switch and wire it up like this, and that controls this big switch, we could put this to the actual headlights, multiple headlights. You'd be like, light up all sorts of headlights. In fact, we would need to do it in parallel. Be like, yeah, another headlight. We can do another headlight. We can do another headlight. Cool? And the relay will be rated to handle that. So if it's on the headlight circuit and they're calling for 20 amps, this actual contactor will be big enough, beefy enough inside the relay to handle the 20 amps. This little sucker over here only has to do 5. Kind of understand the purpose of the relay now? Yeah, a little, maybe. Okay. I don't know if that's totally true, but I'll take you on your word. So that's the overall purpose and quite a bit of the operation of the relay. I think I'll erase everything. And then I'm gonna leave that up because I got a couple images. So if we come in with, let's just say, I'm looking at this. You guys see this right here? What's that say? The ground side. So we could do this a couple ways. If we put B plus right here, you guys all understand that'd be battery. We could even draw it like a battery. Cool, whatever. If we put B plus there, what we could do, you could put a switch right here. See how I put the switch there? Is that switch on the positive side or the negative side?
Negative.
Is it? B plus through the switch. Ah, gotcha. So this would be like a positive side switch. Cool. Power side controlled, you may call it. Right? Because I'm either giving 12 volts or I'm not. If it's open, guess what? 12 volts dies right there. If I close it, what happens? 12 volt goes to here. And then look, ground side is grounded all the time. So it's already got ground. If I've got ground right here on 2, and I just gave it power by closing this power side switch, positive side switch, what just happened to the relay? Bingo, and then it should go like this, click, boom, like that. That'd be like a positive side. All right, but let's just say a lot of the times we won't do it like that. We can, and sometimes domestic do, but the Japanese really like to do it this way. Bring it down. Here's your switch. What's that one? Negative side, ground controlled, ground controlled to like these things. I don't really know. I think that one's about electricity, but this would be ground side controlled circuit. So the way that, the reason that matters to you is like, if it's a positive controlled, when you go to test this relay, you're just gonna be like, put my positive lead here, put my negative lead on ground, and be like, if it's positive side, you're gonna flip the switch and see, does it get 12 volts? Does it lose 12 volts? Does it get 12 volts? Does it lose 12 volts? It should get and lose 12 volts correlating with the switch position if it's a positive side. If you're over here with your lead up here and it's a ground controlled circuit, you're wasting your time. If it's a ground controlled circuit, you just wanna make sure it has 12 volts, but then you really wanna get your meter down here. So this is what I would do. I would take the red lead, I would put my red lead on the B plus, I take my black lead and I put it on number 2 and then be like, hey, Tony, how you doing? Flip the switch, Tony. And when Tony flips the switch, what should happen? I should get 12 volts. I should get ground right here. So see, what I'm saying is if I look at my meter backwards, I put my positive on the positive. If I put my negative on the negative and the meter reads 12 volts, it means the negative's, it's grounded. And then if it doesn't, it's not. So it should be like 12 volts ground, 12 volts, 0 volts, 12 volts, 0 volts, 12 volts, 0 volts. Cool, but if Tony's in there flipping the switch and it's just like 0 volts, 0 volts, 0 volts, 0 volts, then I gotta continue my diagnosis. Cool, but at least I'm not wasting my time up here because I know it had 12 volts there. I know I need to look on number 2. And you notice these are not the correlating 87 and 86 and whatever because this is Japanese. So now partially you'll see why. I don't remember numbers very well. I think it's an IQ issue, but I also don't feel like I need to, so I don't try. I'm just gonna look it up. I'm gonna pull the diagram and I'm gonna know for sure. I'm not gonna be like, well, I'm pretty sure I didn't mix up 86 and 87, because if I did, I'm wasting a lot of time, and I'm trying to bill like closer to $100 an hour, at least 50, even if I'm trying to help somebody out a little bit. Right, so I can't be making dumb mistakes because my memory sucks. I'm gonna look it up. Cool. Now, if you understood what I said, let's say it's ground controlled, and let's just say I'll just help you out. We got ground here, we got positive here. That's magnetized, right? What if we had a little corrosion on this contactor, and it pulls it over, but it's like kind of corroded? What do you think the symptom would be if the load was a bulb?
Dim.
Depends on how much. Dim would be 1. Or if it's really corroded, it could be like not lit at all. We'd have too much resistance right there, right? So how you're actually gonna test this relay in real life is power it on with the ground controlled switch, if that's how it is. Then you can put your meter lead, your negative down here, put your positive on 5, you'd be like, 12.6, bing chillin'. Then you'll be like down to number 3, wait a minute, 4.2. I shouldn't be dropping 8 volts or something in the relay. That relay's no good. But you have to have it powered on. If you opened up the ground side switch and this relay's in the open position, you know you're gonna drop 12 volts right there. You haven't tested anything. You're picking up what I'm putting down. You kind of know how to test a relay. Don't worry, you're gonna test a relay on the circuit boards within the next couple weeks. If it was out of the car, there's another way to test it. Follow what I'm saying. If I took it out of the car and I want to bench test a relay, I need to give 12 volts to 1. I need to give ground to 2. What'll that do? And it should, energize this, magnetize it. It should pull this over. I can then take my meter and do resistance from 5 to 3, and it should have like 0.2 ohms or very little resistance. It should have a good continuity. If I measure right here and it has 100 ohms, that's a problem in the contact. Make sense? But to test the relay, you have to jump. You have to give 12 volts and give ground. You have to come up with that. So you're building a little practice circuit or something.
With regards to these kinds of circuits, how often can we use these techniques in modern cars?
The way, I'd say still fairly often. So like one of the most common times I use this is AC concern. Car comes in, AC's blowing warm. The very first thing I want to know is the compressor clutch kicking on or not? Could it be low on refrigerant? Yes. But I can check the relay operation quicker than I can hook my gauges up and measure refrigerant. So I'm rolling straight over the AC compressor clutch. I'm saying, hey, Tony, turn the AC on and off. And if the AC is clicking on and off, I know that all this side is good. And this is what they do that's interesting. Your AC has a refrigerant pressure sensor over here. And if you have low refrigerant, this switch will be open and it won't magnetize the relay. So if it doesn't click, just based on that quick check, I'm like, all right, I'm checking the refrigerant. But if it does click, I know it has good refrigerant because the pressure switch, kind of like the oil pressure switch, if it's too low, it'll have an open. If it doesn't click, it could be that it's open. I check the refrigerant, but if it does click, I don't care about the refrigerant. It's got enough refrigerant to close that switch. I'm rolling into maybe checking here. Maybe the next step I'll do is go right down to the AC compressor clutch. If the compressor clutch has 12 volts and ground, I know the whole circuit's good. I know the compressor clutch is bad. And that could be over the course of about, depending on how accessible, 10 minutes, And without really knowing that, you're gonna be like, oh, well, first, let me recover the refrigerant and weigh it and see how much you had. And like, there's an hour, there's an hour and it's just a guess, So I actually really like to start at the relay if it's a relay controlled circuit. Now here's the negative that I think you're getting at. If this relay is inside of the fuse box and it's not something you could disconnect, if it's too hard for me to test on terminal 1 and 2, which I generally don't do because I could tell with the click, but if it's more common, I'll test 5 and 3. If it's too hard for me to probe those, I'll avoid it and I'll try to troubleshoot in a different way. But the cool thing is sometimes I can go in with the scan tool and I can actually command this to magnetize because it's computer controlled and I could do some other tests. But if it's a car that's 10 years old, this is a go-to ticket. If it's a car that's brand new, it's a 50-50 because it may be eliminated, which can be a hassle.
Yeah, because I'm just wondering whether you could actually get contact. I mean, you could actually test those points.
Exactly. You're ready right there. So this is what's cool. If on the diagram it has terminal numbers, you can test them. But if you ever see a diagram where there's no numbers in here, that means it's internal.
Yeah.
I can't test it. But if you're working at a legit place and you have access to the correct service info, it should really be leading you a different way to diagnose it anyway. So sometimes I'll just wing it because I know it well enough, and other times I'll be like, I need to really look this up. And on a lot of the ones that they're non-serviceable, a lot of times they'll actually have circuit DTCs. They'll have codes. So if it's something that's non-serviceable, I'm going right for the scan tool. I'm checking to see if there's any body control module codes and DTCs and, different approach.
So basically you will use a scan tool, pull out the codes, and then from the codes,
I'll know a pretty good idea where I'm going. And then I may, let's say I think it's going to be that relay. That's going to be a little bit tough because at some point I will be able to test 12. Yeah. I might not be able to test 3, but if I really have to, this is going to be outside of the fuse box, so I'll at least be able to test there. And actually, I'd probably be able to test 4 and 2 as well, but in this case, I can't test here. But I could test at the top of the fuse. So sometimes it's just like looking at the specific and coming up with my best possible workaround.
Yeah, and see where you can probe and what's available for you to probe to begin with.
Exactly. And the other thing that you guys should know is you're not hired to do magic. Like if there's no test point and you can't test it and you absolutely have to guess, I would just write that very clearly. There is no test point here, and if somebody tried to haul you in court and you stood in front of a panel of experts and I was one of them and you could show me, hey, I can't test at that terminal, I'd be like, well, you're not guilty of anything, you know. So if there's not a test point provided by the engineers, then it kind of sucks. You know, transmissions are like that a lot. Transmissions, you want to test application pressure of the second gear clutch, there's no test port. So I don't know. And I'll write that in my story. I'll write the things I did perform. What I will never write is that I tested at point right here because I didn't, you know. And so it'll still be generally pretty fair. Somebody will say that you're stupid if you can't test it, but it's probably actually them. Cool, so then here's our different types. This is that feedback one. They may call it double throw. The reason they'll call it that is because in the rest position, current will actually go from 4 to 3. Whereas if you give 12 volts to 1 and ground to 2, current from 4 to 3 will break and it'll actually go from 5 to 3. These are especially helpful with computer controlled circuits because what we'll do is, let's say we send 4 into the module, into the computer, whatever ECU type of thing we have, and depending on what the voltage is on terminal 4, it'll know if the relay's open or closed, like as a matter of fact, not kind of a guess. So it'll say like number 4 relay is open, and then when we command it by giving 12 volts and ground to number 2, it's still reading open. It can set a code for that because it's monitoring number 4. So this would commonly be called like you could call it a double throw, but commonly they'll call it a feedback relay. It'll be a relay that provides feedback to a computer, which is cool. The really cool thing is, like Tim's kind of saying, if you want to know the status of that relay, you can go in with your scan tool and you can say, hey, ¿qué pasó, number 4? What's happening there? And it'll be like, you know, terminal number 4 is on or off, and then you'll know if it's open or closed. If it's on, that's open. If it's off, that's closed. So sometimes you can test the relay with the scan tool too on live data. And then here's a solid state. And this relay is drawn this way, but it's not actually how it works. When we get into solid state relays, you're going to picture this. They may even give you this on the diagram, and you'll be like, oh, yeah. But you notice, look, do you see numbers? You can't test it. Part of the reason why, it doesn't even work that way. It's a transistor. It's only got 3 connections. But because technicians understood this better for so long, and some of the old school techs I know, they'll even pull numbers. They'll be like, oh, yeah, it's terminal number 86 is this and 87 is that. What's wrong? And I'm like, man, don't come at me like I don't know. This isn't really how I came up. I'm a little on the younger side. They would remember the relay numbers, whereas the people are like, I don't know what the heck that is if it's a transistor. So they'll kind of like draw this, and then they may say solid state relay or something, and you can't test it at all, which gets us going towards transistors right now. So we talked quite a bit about it. Probably more than enough. So in domestic, you go 85, 86, 30, 87A, and 87. And I'm not ashamed to tell you I don't exactly remember what all these do. Okay, cool. But if you want to know, this is the cheat. You take the relay out, and there's a drawing of the relay, and it has the numbers. So I don't need to remember it when I can do that. So like if you look back here, there will be a drawing. I think I overshot it. It'll look kind of like one of these, except it'll have the 30 and the 86 and 87 right on the relay. Those are cool. And then the other thing that's kind of neat is if you flip the relay over to the bottom, a lot of times 85 will be printed on the plastic. So if you want to test at 85, cool, pull the relay, look, which one's 85? Okay, that's where you need to test. Now another cool thing, in fact, I'm actually gonna hold it, but I'm gonna show you a tool you may consider buying. I don't have one because they didn't have one when I started. So I've learned my own ways to test relays, but they make some really cool relay test kits, and they're not that much money. And if you wanna be able to test relays, I'm gonna show them to you. So here's, and PS, remember I was saying sometimes the relays have protection devices. So if this is the AC compressor, we're worried about that voltage spike. It's like, hey, voltage can drain back this way, but voltage can't spike back that way. That diode can sometimes be in the relay, or sometimes it's separate from the relay, and it's something that you can replace individually. It depends. If it has the diode on the original relay, it'll have different terminals, so you can't just put a non-protected relay where there's supposed to be a protected one. Cool, and sometimes there are even resistors too. And that's kind of what it's saying. The large spike, when you, especially if it's something that's a lot of amps, like AC compressor clutch, when you open the relay up, it can actually cause like a spike, a surge, and the computer don't like that. Cool. So here is, this is a standard controlled relay. I think I'll draw. This is definitely something I want you to understand. Come on, sweetheart. Okay, you guys know what that symbol is, right? Now? Okay, so is it safe to say 12 volts comes out, goes in, does its thing? We could say safely that we're going to have 12 volts here. As it sits right now, is this switch open or closed? So that means ground should come up. We're going to have a whole day on tracing circuits, so don't panic. Okay, which means, what's that doing? Wah, 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 wah. Yeah, it's doing some work, which means this pulls over. So what happens here? Shouldn't it go across the bridge? And, cool. So what should happen to those? They should light up, exactly. So we are controlling this headlights with this switch. Make sense? Right here, we may have 5 amps. Right here, we may have 20 amps. Again, summarizing the purpose of the relay. So there you go. So if I wanted to test it, again, there's a lot of different ways. Let's just say the lights aren't working. Maybe the first thing I would do, put my hand on this relay and say, hey, Tony. What am I going to have Tony do?
Turn on.
Flip the switch. And if when Tony does this, forward, back, what should I feel here? Click, 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 click. If I don't, what's that tell me?
It's not working.
True, but where am I testing?
No.
Do I want to test over here?
No.
If it's not clicking, our problem's on the control side, see? I already cut the problem in half. I don't need to test all this baloney. I need to be like, oh, the relay's not clicking. Let me check to see if it's got 12 volts here. Let me check to see if it's got ground here. Hey, there's no ground right here. How that would look, by the way, if this switch was open. Yeah, that one's kind of shot. If this switch was open, 12 volts would actually come through this. I would have 12 volts going in and 12 volts coming out. And 12 volts would go all the way to where the switch is. So like I could troubleshoot that it's the switch, you know, by probing here, probing going into the switch. I'll be like, why has it got 12 volts on the ground side? I'm gonna tell you right now, if it's got 12 volts on the ground side, that means the ground is open. I'll tell you, one shot, pow, ooh, 12 volts on the ground side, ground is open. I know my problem is here. I don't care about up here. I don't care about over here. I'm not gonna spend any time diagnosing any of that stuff because it's just simply the click test and then one measurement. Make sense? All right, so what if I were to say, Tony, do the clicky thing, and then it were to click. What does that tell me? Click, 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 click. That means this is getting magnetized, right? So what's that mean I'm getting down here? Come on with me. If it's clicking, I got 12 coming in. Ground, yeah, exactly. So that means my switch is good. Now, if that's the case, I don't care about this control side of the circuit. I'm focused more on like the load side of the circuit, you know, the high amperage side of the circuit. Cool. Then I could be like, let me test here, let me test there, right? So that's how you go about these. I think if you kind of get it, when I put you on the board and you build a relay and you could do your own tests, you'd be like, oh, I really get it, right? And you could do this all like one class period for the theory, one class for the lab. That's pretty good. I see a lot of people struggle with that still. All right, now this is different. Remember that switch? Who was turning the switch on and off? Tony, how you doing? Well, Tony's fired. You know why? Because I'd say, hey, Tony, turn on and off, and Tony didn't do what I wanted. Sometimes Tony would turn the lights off when they shouldn't be off, and so instead, I fired Tony and I hired AI, artificial intelligence. So here you go. We've got I'm not going to do this, a PCM And if you look, the PCM is controlling the ground. We send 12 volts to the coil. What provides the ground?
PCM,
What the heck is that?
control module.
Yeah, powertrain control module, or you could even make it an ECM, just an electronic control module, or some kind of computer. You know what this computer's job is? Give ground or don't give ground. This computer replaced Tony. You understand? Tony no longer needs to flip the switch. The computer will flip the switch. However, remember, computers don't, it's artificial intelligence, not actual intelligence, okay? They're different. The computer needs to be programmed what to do, when to do it. Make sense? So if we have a whole bunch of sensors, look at this, start and run signals, different sensors and whatever, those sensors need to see the correct criteria, such as, if you're trying to turn on the AC because it's, I don't know why you're turning it on, because this temperature says it's negative 40 outside. It's going to be like, yeah, good luck, buddy. I ain't doing it. You'll be like, Tony, turn it on. Tony's going to be like, Tony's gone. It's me, AI, and it's negative 40 outside, so I refuse to turn it on. See, so the computer can override the system. Skynet, you know what I'm talking about? Too young, Skynet, right? Yeah, Terminator. Yeah, exactly. So if the computer says what you're trying to do is stupid, Tony, it just says no. Have a nice day. So if you get a system like this, you're gonna be like, hey, is the relay click? Yes or no? Then probably what I would do, go right with the scan tool, see if you got codes in the module, and be like, hey, what's up? Why aren't you doing what I'm requesting? And you may get like, hey, I've got an ambient temperature sensor fault. And if it reads negative 40, it's going to inhibit, which means block, the ground provide to make the AC compressor clutch turn on. See, so the diagnosis is similar, but different. And it's not so much with the meter. It's more like, let me get the scan tool. Let me start doing some stuff. Sometimes you can go in with the scan tool and you can be like, AI, knock it off. Turn that clutch on now with the push of a button, and it might do it. And if it does it, this wire is good, this is good, all this is good. You know that it's probably getting like a bad signal from one of the sensors. So our diagnosis has totally shifted away from the relay, away from the motor or the AC compressor or whatever, and more start and run signals or air conditioning inputs or signals, sensors. Make sense? I gave you a whole lot pretty quick. That ramped up, didn't it? All right, but this is a logic-controlled relay circuit. Point being, the PCM logic controls it. Secondary point, there will be a transistor in here, and the transistor will give ground or not give ground. Make sense? All it needs to do is give ground or not give ground. That's the PCM's role in this circuit. When should it give it? Depends on the programming. So if let's just say the engineers found a good reason why we should run the AC at negative 40, they could go in and rewrite the program and be like, yeah, I don't care if it's negative 40, put the AC on. It's your funeral. And then all of a sudden, boom, it would work. Even though it might have a bad temperature sensor. Cool. The programming gives it permission or not permission. That's the logic. Makes sense? I give you a whole big thing on input, process, output, but I'm gonna chill it down a bit. Cool. Operational check. All right. This is like a little mini test. Ungraded for you, but for the people who get the video, this is gonna be a graded question. You're lucky. Here we go. All right, you can see where the lead is. You can't really see the volts, so I'll rewrite that in. This is chassis ground. Right here, I'm gonna draw in a bulb, which I'm gonna send to ground. Okay, if with my relay right here, I'm getting 0 volts, I want you to process this information for a moment and tell me what you can tell about that. What can you tell? If I'm getting 0 volts there, what's going to be the status of that bulb? 0.
No.
Bingo. So the first thing is, hey, this bulb is in op. And you went to it, and if it doesn't have 12 volts, it's no good. Let me say I worded it different. Let me tell you it had 12.6 and the bulb doesn't light. What wrong?
The ground.
Wait a minute. Let's actually technically Technically, you don't exactly know. So if I had 12.6, it could be the bulb or the ground. You're actually correct. So let's just say I moved my black lead over here. And it read 12.6.
Bulbs on.
Bulbs out. Done. Period. Your diagnosis is over. I'll prove it to you. If I've got my ground on here and I've getting 12.6, that means this ground is good and this positive is good, period. That bulb is like a bad employee. You gave the bulb everything you needed. Here you go, bulb. Here's 12.6. Here's ground. Do your work. And it's just like, time to, it's termination Tuesday. Bulb, you're fired. Take the bulb out, put a new bulb in. Now let's just say you put a new bulb in and it still didn't work. And you rechecked your numbers. Well, that wouldn't really make sense. But let's just say in a different car, you rechecked your numbers and we're back to where we were, 0 volts. All right. It's not a bulb, would you agree, if it said 0 volts? So what do you think you'd want to measure next? There's several measurements. Right here, there's not necessarily a wrong answer, FYI.
The switch or the battery.
All right, so if I wanted to measure, let's just say, I didn't put a switch in here, did I? I'm going to make the switch a ground side switch right here. Cool. If I wanted to test the switch, how would I do that though?
Close the switch and test it.
All right, close it. I agree. So now I'm going to make it closed. And then, see my red lead right here? I'd actually leave it. And I would take my black lead, and if I put my black lead right, let's say here, or actually better yet, even here, if I put my black lead on 4, what should it read? That's true, and you understand why, right? Because I have my positive on a known good. The other way I could do it, I could put my positive up here from the battery, and I could put my negative right here. And if it has ground, you're like, oh wow, if it's got ground, what's that tell me about the switch? Switch is working, that's good, it's happy switch. So that means this side, good. In one measurement, this side, okay. Then I'll be like, all right, what if I kept my ground here? Now it's a known good, right? And real quickly, I took this red one and I put it right here. What should I get? 12, yeah, full source voltage. What if I got 0? Here's a term, ready? Generic term, no power. Make sense? It's not getting positive voltage, right? Right here, if it's reading 0, there ain't no power there. Make sense? So now I'd be like, oh, let me test. And then if I went up here, let's say right here I had 0 volts, but then right here I had 12.6. What's wrong?
Wire.
Yeah, exactly. So you'd be like, hey, this doesn't need a relay. This needs wire repair. Now the problem is, so you know, on the car, this may be long. It may be in a big old loom of wires in the conduit and around and under and up, and so it can be hard actually to diagnose an open wire. But if it's an open wire and you replace a relay and you replace a bulb and you replace all this stuff, you're messing up. You know, that's not. If it takes more diag time, because I had a car at one point, the daytime running lights didn't work, and I ended up spending like 3 hours diagnosing an electrical problem. You think I'm pretty dumb, huh? Remember the eagle? Ah! All right, that was me. But you know why? I needed to test a wire, and the wire was behind the bumper cover. I did all the tests I could, but it was actually this wire right here. I could test at the bulb, it had no 12 volts. I could test at the relay, it had 12.6, and it had 0. So I was like, hey, it's the wire. And they're like, all right, what's the fix? And I'm like, I don't know, it's behind the bumper cover. I could test it at the fuse box and I could test it at the headlight, but it goes from the fuse box through the body, up and around, whatever. It took me like over an hour to get the bumper cover off. Then I found the problem on the wire, you know, and then it was sort of like I had to actually really measure the wire, and the wire's long, so I'm like testing here and checking and pulling. I know it's between here and here. That's the most diagnosis you can really do with your meter. If you want to know if it's between here and here, you'd have to stab the wire, which you just kind of ruined it, right? So I was going very carefully, and I was like, hey, come to find out actually what happened. It's an old school car, Pontiac Sunfire. You ever seen them? All right, kind of embarrassing, but cool car back in the day. As long as you're a female, it's totally fine. It's legit. But this car had a recall and they had some sort of problem, like when the cars were brand new, like 1 year old, and they had to actually open the harness up and do something with the wire. And the guy working at that Pontiac dealer at the time, is going way back. This is 2007 probably. And he's like, and I found it and I was like, how the heck did this wire get cut behind the bumper? How'd somebody get in there, you know? And I was just shocked because I was kind of new, a little bit more of a rookie tech at the time. And he came and he told me, he said, hey, look, there was a recall on those, you know, and I was here back when they were new, like in '02. And when they came for that recall, you know, we just grab our razor blade and just zip it right down the line to open the wires and then do our thing. So his razor blade pierced the insulation, and it took like 5 years to that wire to really totally corrode. You know, so I was like, oh, okay. That's what you call two-legged varmint damage. Right? So he's a varmint with 2 legs. What kind of varmint's got 2 legs?
Paul,
Yeah, the mechanic done it.
question. Now, in a situation like this, how do you practically get very long leads on your meter? Because my meter leads are like that.
True. Okay. Well, there's a couple options. They actually sell. Let me show you a couple quick things, because if you understand the theory, now what you're left with is practical application.
That's right.
So what I want to show you is a relay test kit, and then also DMM lead extension.
Yeah, I mean, if you're getting like a Flow 88 or something.
Yeah, they're short.
Yeah, they're really short. They're like 3 feet at best.
Yep. So now I'm not
okay.
saying Harbor Freight, but I'm just saying this is 30 feet. So you connect your black lead, you connect your red lead, and now you got all the car's 25 feet long, so you're good on this. That's one quick one. So it's like, the only thing I would probably do on this is I would fuse these, because I'll tell you embarrassing, honest story. I had a set of these and I no longer have them, and I didn't lose them. And I mentioned fuse because I did a test at one point, and then I think like I had them going through the door or something, and when I shut the door, it actually grounded them, and they're not fused, so it burnt the crap out of those things. They got fried. It burnt this plastic and all that type of stuff. So the only thing I would do is if you can find fused one, that'd be better. If you can't, I would maybe add a fuse yourself, just in case you do what I did and shut them in the door and short it to ground and then catch them on fire. Kicked them across the shop floor, so no damage to the vehicle. But the leads died that day, and I never did get new ones. I probably should. So that's one cool option to do those tests. Another one, here on this relay test kit, is kind of a nice tool. And the reason why this one doesn't show, okay, this one's more for inductive, so that's not actually what I'm looking for. There are relay testers.
Oh, Lau has one, huh?
Yeah, and Lyle makes pretty good legit stuff.
Yeah. I buy a lot of Lau stuff.
All right, so let's see.
Master relay jump here.
All right, this is the perfect image for this. Let me just get so you can see clearly. Because remember, we got those numbers, right? 86 and 87 and 30 and whatever, or 1, 2, 3, and 4, etc. I actually do not know the backstory on why the numbers are the numbers. I promise you I have no idea. But if, let's just say, you're trying to test those wires, it's hard to test them with the relay in. You got to take the relay out and then probe them, and then you can't put the relay in. This is basically like a test pedestal. You'll pull the relay, put in the tester, put the relay back in, and right now you have 1, 2, 3, and 4, or 30, 86, 87.
Breakout board.
It's basically a breakout box or breakout board.
Yeah,
exactly.
That's what it is.
Yep. And so this is a good tool to consider if this is the type of diagnosis you're doing. Remember I told you I don't have this. When I was, learning the way, they didn't have this. So like I kind of learned my own different way, but actually I would like to maybe get one. It's just, you teach old dog new tricks, and it's sort of like, nah, I don't need that trick. I got a lot of things that I can learn, and I'm just not putting the energy into learning this new, different way. But it's a good thing to consider for all those same diagnoses we just talked about. So any point you want to measure through this, if you have the relay test kit, you can hit any of those points. And if you can hit this point, this point, this point, this point, you can really pretty much know what you got with that circuit.
So basically, you actually need to have the different form factors.
They come in the kit. They come in the
adapters
kit.
to be able to
Yes.
put in that.
Yeah.
board.
Exactly. Especially the domestics tend to be one way, and the Japanese tend to be one way. But that kit came with like about 4 or 5, 6 of them, depending on the kit.
Okay.
So that's a nice one to consider if this is where you're getting really serious.
All right. So the Lao one, huh? Okay.
I like the Lyle one, but you could probably also find some, Chinese one that would be, no offense to, any particular Chinese engineers in the building, but I'm just saying, like, you could get a lower cost one. How about, let's just make it Harbor Freight. You could probably, I don't think Harbor Freight sells it. Harbor Freight is not really the diagnostic tool supplier. It's more like they sell hammers and bigger hammers and wrenches that you use as a hammer and hammers that you use as a wrench. Pretty much.
Exactly. I call it one.
Nah, ASE would sell a meter, but ASE won't sell a relay tester. Yeah. Neither will Home Depot either. All right, and then here's even some relays that have time delays. I don't really see these commonly, but some people, let's say you built a cool car with an eBay turbo kit. Okay, now you see I'm really stretching. Notice I said eBay turbo kit. I didn't say the country of origin. So you know where it came from, though. So you put that on the car. What's nice with a turbo is if you do some pretty high revs and some heavy load, that turbo gets hot, the oil gets hot. If you come right off of a pole on the drag strip and you shut it right down, that turbo's still really hot. It tends to kind of cook the oil in there. It gets hot. It's not good for the bearings. Be actually better if you came to a stop and let it idle for 10 minutes, sometimes like 20, 15 maybe. Well, you can put a relay like this on your system. We'll call it like a turbo timer. It'll keep your fuel pump going. It'll keep your ignition going. It'll keep your ECM powered up. You could literally shut the car down and walk away, and the car will just be sitting there running, doing like a cool down cycle for however much time. It probably wouldn't really be as simple as a relay. It'd be like a box that has a relay inside of it. So that's a cool example of why you might. They also used to have stuff like this on the old cars. When you'd park it, it would keep the headlights on for a certain amount of time. Now they're going to do all that through the ECM. If you wanted a car that could do turbo timer, keep the headlights on, whatever, the control module can be programmed to do all that stuff. But back in the day, it used to be that. Cool. Delay it on, delay it off. All right, so relays are a big thing. All right. But we got a lot of stuff to cover. There's a lot of components. So we're now on to solenoids. Solenoids and relays. If you understand a relay, a solenoid's actually probably easier to me. Because solenoid's an electromechanical device that converts electrical energy into mechanical linear. So that means magnetism. But rather than swinging the relay contactor like this, it moves it through the core like this. Okay, but otherwise it's kind of the same concepts. If it's simple solenoid, insulated wires wound many times in a hollow cylinder, and there's a sliding mild steel core. So this is key because steel is ferrous, which means it will attract or repel based on the direction of the magnetic field. This wouldn't work with like aluminum or something. But if it's a ferrous metal, such as mild steel, and we magnetize it with the polarity positive on the top and negative on the bottom, maybe it'll move it up. And then if we switch them, now the negatives on the top and the positives on the bottom, it will move it down. Make sense? So we can do, again, it's a load in the system. We could do work. Most common to me, the power door lock. Ready? Junk, 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 junk. It's amazing. You could have done it with your hand, but you could do it with a button, and that is why it's so entertaining to small children. Cool. So that should mostly make sense. Here's some of what they look like. This is most likely, I believe, this is a transmission shift solenoid. But sometimes it's hard to tell because the solenoid can look one way or another way. I actually think that most of these are mostly transmission parts, but we also have them for emissions things. So if you had your car and the gas was evaporating in your driveway, it goes into the vapor canister, the charcoal canister, and at times we want to do what's called purge that, which means empty it into the engine while it's running. We could use a solenoid for that. We'd have vacuum going to one side of the solenoid, and if the solenoid's non-energized, the vacuum is not passed through. The engine sucks on it, but it's like, nope, you ain't going anywhere. But then if the solenoid is energized, it moves the iron core because it's magnetized, right? And then vacuum's able to draw on that charcoal canister, and it basically sucks out all the vapors. Pretty cool, right? So we can leave the vapors with no 12 volts in ground, or if you apply 12 volts in ground, it'll allow the vacuum to draw the vapors out of the canister. And if you have a problem with that system, by the way, you get a check engine light, you fail smog, you can't get it registered, you can't drive your car, straight to jail. Straight to jail. But that's why, you go into the smog ref, we can hear them from here. But that's why we have this system designed. I mean, I'm not super excited about emissions, but I gotta tell you, like, emissions are a big part of our job, and I've come to not be so anti-emissions because, you know, it's good for the environment. I'm not super self-righteous with that regard, but when the cars come in and they have a problem, generally, I can fix the car cheaper than they can go pay for the Chuerco smog. So those smogs for $350 or whatever, if I can fix the car for $300, I got the business. And if this part right here is $20 and I could diagnose it in an hour, you know, I probably just really charge them for my time. But I'm just saying, like, this is not bad for the professional tech necessarily. Makes sense? So if you understand it, make short work of it, you're worth good money. It also means, like, you know, if you can understand this type of stuff, you can go past, you know, you could pass the A6 electrical, but A8 engine performance and L1 advanced engine performance is a lot of this. You got to understand this, not only electrically, but also mechanically, right? So it starts with electrical. If you understand that electrically, that's a building block for the engine performance. If you can pass A6, A8, L1, 3 ASEs, L1's a beast, though, I'm not gonna lie. L1 is advanced engine performance. That's a beast. But if you pass it, then you go take a smog class and you pass that exam, you're a smog inspector. They make pretty solid money and they do not work that hard. So I'm giving you a path, especially if you're, you know, looking to do like a little side thing on the weekends. Be like, hey, I got a smog license. Do you have anybody to do smogs on Saturday? You know, I'll come in and work $300-400 on a Saturday. Pay me cash. I'll punch out as many smogs as come through the door. You know, that's 400 4 weeks out of the month. You know, you're talking $1,600 a month extra for just a Saturday every week. You know, I might even go for 500. You know, and you get it because there's not that many people who can pass those tests. Okay, so kind of just selling on the fact that if you understand this electrically, you have the potential to understand it both electrically and mechanically later. Then you have the potential to go and pass those tests to be worth the big bucks. Cool. And then another example, an injector. I was talking about the injector before. Right here, this is the pintle and it's down. We're trying to send fuel through here. The solenoid's right here. The fuel is blocked, but if we activate this winding, it lifts this pintle up, and what happens to the fuel? For how long? Depends. The computer controls the on and off time. It'll say pulse on for this much time, pulse off. If it's duty cycle, it'd be 50% on, 50% off, 50% on, and then you see this Mustang coming up, kind of like you see them out of the corner of your eye, and they're like, and you're like, let's go, and you mash it. It ain't gonna be no 50-50. It's gonna be on like 99 and off 1%. You're gonna spray more volume, right? The on and off time of the solenoid pulses the quantity of fuel. The more gas, the more power, right? The more you're gonna win. You better not lose that Mustang.
Paul, second question.
Shoot it.
This is a GDI related question.
No problem.
Now, given that most engines are GDI right now,
PZO.
Are these solenoids, do they wear out faster because of the pressures? Cylinder? I mean,
Good, a little above the class, but I'll take it. So this is a solenoid. Solenoids are fine, but you guys remember in the early week we talked about those crystals, the piezoelectric crystals. Solenoids for GDI, because they're running 4,000 PSI, and on the diesels more, by the way, that's pretty hard on this solenoid. So this is what they'll do on a diesel. They'll do a fuel injection control module, and they'll bump these from 12 volts to 48 volts or something. And that way it's actually got more power, right? Because it's gonna have more volts, and that's gonna be the power equation, volts times amps. So if you do more volts, they can have more power. They'll take it pretty well. But they also have the piezoelectric injectors, which we give a fairly small amount of current through, and the crystal will expand, and that will actually prop this open and spray. So if it's on GDI, we do some solenoids, but a lot of stuff we're getting away from solenoids and going to like piezo injectors and stuff.
So
For that
this
reason.
is to allow the injectors to last
Yeah.
longer as
Yeah.
opposed to wear out.
Exactly.
Otherwise, the pressures in there will just.
It's extreme. The GDI systems are still having some issues, like fuel pumps having to work that hard are failing a lot. The injectors tend to be decent, but they're not your typical injectors. They're beefing them up. They're like 5 times the price for one injector.
70, 80,000 miles and they fail. I mean, typically
Yeah.
Honda or
Yeah.
they fail. Just
And it's all in the positive of the gasoline direct injection. We're spraying fuel directly in the cylinder. That means better emissions, better for power. That's really about it. Negative being it's very hard because now we're not spraying it into the intake and letting it get sucked in. We're overcoming the compression in the cylinder. So we got to bump up our pressures, beef up our injectors, beef the stuff up. That costs the common consumer more money, So I'm not really in the position to be like, hey, this whole piezo thing, this whole GDI thing is a scam. You're increasing fuel economy and reducing emissions, but you're requiring the manufacturers to build a more expensive car. That's not really my role. My role, know how the system works, know how to diagnose it. But if somebody were to have an argument with me about it, I could at least present the facts as a subject matter expert. That's, if you're trying to follow my path, that's what you should do. So I got my own feelings. Mostly I'll keep them to myself. But what I also have is the facts. So when people say, oh, the cars are too expensive, the manufacturers mark them up so much. Actually, I think the manufacturers are making less per unit than they did, but they're building cars to a standard that's imposed by someone who never knew how to make the standard. They come up with a standard, they're like, hey, average fuel economy needs to be 45 miles per gallon by 2025, I think this year. Don't care how you do it, make it happen. And they're like, we'll make it happen, but we're gonna do this new system, that new system, that new system. And now you're like, hey, can I have a basic reliable car, 24 grand? What? Back in 2009, I bought my Kia Rio for $8,888. What happened? Well, quite a few things happened, but one of them being this new tech costs money. The positive, though, they're pretty good on gas, so take it how you want it, but at least you know kind of like how it works. Cool, and so we got lots of different types of injectors, but solenoids don't stop there. We got those emission solenoids for evap. We got the transmission shift solenoids, etc. The general consensus, though, is if you send 12 volts in and ground in, magnetizes, opens, and some fluid passes through, if it's a solenoid like that. If it's a door lock, 12 volts in, ground at the bottom, clunk, right? It does some work that involves a linear movement, like the door locks, or like a pintle to spray the fuel, or like a pintle to allow vacuum, or like a pintle to send fluid to the second gear clutch, whereas before it was blocking it. It's like, hey, you're in first. Okay, now it's time for second. Boom, open the shift solenoid, send the fluid to the second gear clutch, and then bang, you're in second, right? So solenoids. If you get solenoids, I just gave you 3 different ASE subject areas that you can more or less diagnose, or at least be way ahead of the game, but you gotta understand the solenoid first. Cool, pretty good. Here's another actual fun one. The horn I don't commonly think is a solenoid, but it technically is. When you press the button on your steering wheel, that grounds that terminal on the ground side of the relay. So it's got 12 volts all the time. We ground it. That magnetizes the coil that pulls the contactor over. That's a relay. From there, it sends 12 volts to a solenoid, which this is going to actually vibrate. It's going to go down, up, down, up, down, up. See, down, up. When it does that, it's going to pulse these metallic, like it's almost like a little fan blade. They don't spin, they go up and down. When it does it that fast, you can see that, and this air gap's going to get tighter, further, tighter, further, tighter, further. It'll do that so many cycles per second. Remember, cycles per second is frequency. Remember that, kinda. If it's high frequency, anybody want to demonstrate high frequency? You're welcome. Thank you very much. Okay, so if you want a high note horn, you pulse this frequency fast. If you have a truck, is that what you want? No? If you have a truck, you want to kind of be like, that's a low frequency. They control the amount of on and off of this solenoid. That's literally your horn. And then when it does that, these little blades are going to pulse the air, and the air is going to actually pulse your eardrums, and you're going to be like, oh yeah, I hear that. Like that. It's pretty cool. So that's another one. Okay, now motors, and we're going to get a little ways into this, and then you're probably going to be hurting. So we'll take a little time, and then we'll come back. But motors are cool. When I say motor, let me clarify. Who's thinking NASCAR? Start your what? Yeah, don't say motor. Okay. So if we're talking in the backyard and you're like, oh yeah, the motor in that thing's pretty good, like I have to know the context of our discussion. Whereas if I don't, you really need to call it an engine, okay? If it's pistons and heads and valves, that's an engine. If it's a motor, that's like more of a, they do have things other than electric motors, but generally in automotive, if you say motor, I'm electric. I'm thinking electric, you know. Tesla, electric motors. Mustang, no. Gasoline engine, make sense? Different. Yeah, I heard that's true, but let's just leave that one right where it's at.
Yeah.
All right, so I could have gone with like the Challenger or whatever.
Not anymore.
Oh, got him. It can make a frequency, you can custom tune it with a speaker. That's a solenoid, okay? But if you overall consider motors being electrical, they take electricity and they turn into rotational movement. That's what an engine really does, right? We put gas, air, we compress it, we spark it at the right time, and we get a push down, but the crankshaft turns it to a spinny thingy. A spinny thingy is what we're all about. If you got a rotational movement, that drives a transmission, that drives axles, that drives wheels. So if the car is going to go, it's probably going to be an electric motor. You could maybe make a car move by solenoids. You can make it hop. Like solenoids go up and down. You make it jump down the road. It would make no sense. Rotation is motor stuff. Now how? Not that different than the solenoid actually. The solenoid, remember how it can attract and repel magnets? That's how it's working. The motor, interesting, uses magnetic fields to create rotary motion. Two main components, the armature and the field. And now we could go really in depth on motors, and I know enough to probably make you feel like pretty good, but a lot of the intricate details don't totally matter to us as the technician. If you know well enough how to diagnose it, you don't necessarily need to like flex and be like, oh, this is a permanent magnet motor, or this is a pole shoe motor, or whatever. Cool, so I'll still show you, but this is one of those things where if you're taking my advice, I would not study real in depth the type of intricate details of the motor. They've changed over the years. They've gone one direction and kind of back, but the basic function's the same. The way we diagnose is pretty similar. So the armature contains electromagnetic coils. The field contains either electromagnets or permanent magnets. That's the difference between a pole shoe and an electromagnet right there. What's it matter to you? Not freaking much. You take it out, you bolt it in, you make the connections. That's, if you're designing it, I need to sit down. This is not what I do. This is not what I know. I don't, Tim might have to take over. You know, this is just not what I really do. You probably know a little more than me, which is totally awesome. So, and then if you see, armature coils can be energized and create electromagnetic fields. Those fields can be turned on and off to attract and repel. And right there, that's the important thing. Turned on and off to do what?
Propel.
Attract, repel, attract, repel. And they're going to alternate, right? If there's a magnet right here and I attract it to me, but I want to keep it spinning, what should I do? Poof, repel it that way, right? Attract it to me, repel it away. Attract it to me, repel it away. So when you see these motors, you're going to see a lot of attraction and repulsion over and over and over and over. And it's going to be happening, we'll focus on it in one spot, but it's probably happening in 6 or 8 different places because we're increasing the power of that motor. Cool? And then they are attract and repelling fields of the stationary magnetic fields. Okay, so there's one thing that's moving and there's one thing that's still. So sometimes right there, what I'll say is I'll go to the stator and the rotor. And the reason I like those terms is because the stator is stationary and the rotor is rotational. So sometimes if I switch to stator and rotor, just be like, oh yeah, it's, you know, you could get into detail about armature and whatever, and that's not generally the word I'd use. So let's go with like inductors in general, by the way, because we talked about inductors. This is your solenoid, cool. If we magnetize this, it makes the attract, it makes the repel if we switch the polarity. Okay, cool. So I just showed you something. How do we make it push and then pull? This is a term, what I just did with my hand right there. Reverse. Flip it's good. Reverse polarity is the technical. So if we are reversing polarity, we're attracting, repelling, attracting, repelling, attracting, repelling. So I just gave you a clue when we get into motors, we need to have it switch polarity. And it needs to switch polarity fast to make it spin fast. Cool? So that's induction. Now when we get more into the motors, we're doing that same thing, but on a little bit more of a complex scale. So let me pause right here and just say, if you took a battery, it could be a C, a double A, whatever, and you were to put a little paper clip and not touch the nail, but go around the nail and then to the negative, if you connected the positive and the negative, it would magnetize this nail and it would pick up these paper clips. What do you think would happen if you broke the connection right here? Exactly, no longer magnetized. So I'm showing you if we have current flow, let's say positive, negative, around, the more roundy rounds, the stronger the magnetic field. That's an electromagnet. Is this nail magnet a magnet? It's an electromagnet. It's a magnet while it's touching, but it's not a magnet when?
Disconnect.
Exactly. So when you hear the term electromagnet, that means something that you can magnetize and then unmagnetize. Demagnetize, probably a better word. Cool? What do you think about a permanent magnet? That's the magnet that goes on the fridge. It's magnetic today, it's magnetic tomorrow. You don't have to, you can mess them up, but you don't have to send any current through it to get the magnetic property out of it. Does that make sense? So when you hear permanent magnet motors, don't be like, what the heck? Like, it's not a big deal. It's not. We just don't need to do the electromagnet deal. They're already magnetized. Cool. So we jump in. There's lots of examples. They all use electromagnetism, including the electric clutch. So if this is magnetized, it draws the clutch in, it drives the guts of the compressor. So that's kind of beating the electromagnetism a little more than I really need to. Here's your first basic motor. So if we look at this, I'm looking, let's just say, let's make these permanent magnets, right? There's a north and a south. These magnets are like flipped 180 from each other. And then these coils, when we magnetize these, let's say right now, this one is being attracted to this north pole. And this one is being attracted to the south pole, which also means technically south is repelling the yellow, north is repelling the red, but also north is attracting the yellow and south is attracting the red, right? So at least when it gets to a certain point, it'll be less of a repel and more of a attract. Cool? So if you look at this right now, if we didn't do 12 volts in ground, this thing's just sitting here because these are not magnetized. But if we give it 12 volts in ground, like that nail, what happens? It magnetizes. So that's going to make it try to turn a little bit. But then think about it. If the yellow is really attracted to the north, it's going to get like as close as it can and it's going to stay there, right? So what you want to do? And yeah, oh, I like it. I like it. See, so did you guys hear what Tim said? We're going to stop the positive negative, and how about we make it negative positive? Remember, it was attracting. What happens when we make it negative positive? We flip it. What's it going to do? Yeah, repel. Now what do we need to do again? Attract, repel, attract, repel. If you get that, you're mostly there. But the thing is, we'll do this with multiple sets of field coils. We'll do it with multiple, right? 2 is fine, but do you think 2 is going to give you like the most smoothness? Because right here it's kind of weak. It's trying to draw it in and then it's strong, but then once it gets distant, it gets kind of weak. So we're going to have them spaced tighter. And depending on the motor, we can have a different number of segments in there. Okay, so far kind of decent? So think about this. If you were to hook up 12 volts and ground to a motor, you'd think it would only turn like maybe a quarter or half turn, huh? But it doesn't. It keeps going and going and going. And that's because the positive and negative switching, it doesn't have to occur outside the motor. We can have it occur inside the motor. And that's when we get into these things with commutators. Cool, so generally we're gonna break it down into DC and AC motors. So DC motor converts what type of current?
Direct.
Freaking DC. That's why it's a DC motor. So that's normal. Your car's got a DC battery, right? Your car's got an alternator that is inverted to DC. So on the normal vehicle, we're dealing DC. Now, if I just mentioned DC motors, you know I'm gonna have to bring in AC, right? But like, don't even be tripping, we're not there yet. Just for right now, we're just talking DC. These are the more simple. Okay, blower motors, power window motors, fuel pumps, you name it. Pick a part on the car you think might have a motor.
Seats.
The seats, yeah, yep. Windshield wipers. The trunk sometimes is a solenoid and sometimes a motor. It's kind of interesting. The trunk, when you pop the trunk, sometimes it's a dunk solenoid and other times it's a motor that moves a gear out of the way. It could be either one. Cool. You could probably think of tons of stuff. All right, who knows what a CD is? Compact disc. No, you don't, do you? Where do you pay for the streaming service on that CD? I'm trying to figure that out. Okay, but you used to put these things in the car and it would grab it and it would spin it. There's a little motor spinning that CD. There's motors all over the car. Anytime you want. And then see, if you go way back when it didn't work, you'd have to take the cartridge out and go and put it back in. Then you'd have to take the CD out later and clean it like this and be like, oh. And now you're just like, Mom, what's up with the Wi-Fi? I can't stream my game. Everything's changed. I don't understand this world. All right, so DC motors do all sorts of stuff. They could be permanent magnet, series shunt, compound. Like a lot of these details, I have an overall understanding. I don't even really try to get a really in-depth one because in our line of work, the car comes in, the motor doesn't work. The seat doesn't move. I diagnose it as either the motor or the wiring or the switch or the fuse, right? Does that line up with what the heck I've been showing you? Because I set this up. So if I'm teaching the wrong stuff, I need to be fired. So if what you're gonna do is design motors, I'm not the dude to do the class, cool? But whether it's one of these or another one or whatever, my neighbor has an RV, it's a big one too, it's a really nice one. Like, you know, some of those RVs can be like hundreds of thousands. So it's like hundreds of thousands. It's actually a big pile of crap if you ask me. I'm not even gonna lie. But he goes to get out of the seat and the steering wheel that telescopes, he went on a long trip to Phoenix and he had the thing like rested right down, you know. He goes to get out, it won't move. And he said, hey man, I tried to figure out my steering wheel telescoping motor. I couldn't figure it out. Can you help me out? And I'm like, oh, let me see. Is it a permanent motor or a compound? No. I went and got my meter and I was like, his name's Rod, but let's call him Tony. Hey, Tony, push the switch. And I check it, and guess what it's got? 12 volts and ground, but it don't move. What's my diagnosis?
Change the motor.
That's it. See, that's what we do. And I told him, he's like, are you sure? And I was like, yeah, I'll prove it to you another way. Let's jump power and ground right to it, and it won't move. Let's bang on it a little bit. Sometimes you bang on it, if it's got like a little bit of damage on the brush or something, it'll actually free it up for a second, right? So I showed the homie all the little tricks, and he was a little sketched out, but he just sent me a text. I'll even show you, but it's on my phone. Hey man, you'd be so proud of me. I got the motor in last weekend, because it's a holiday weekend, President's Day, right? Which, you know, it's Valentine's Day. Valentine's Day weekend now. He's like, I soldered the wires in, it works now. And I was like, yeah, that's awesome, but like, obviously I fixed it. Remember, we diagnosed it. We didn't guess, we measured it. We measured it 2-3 different ways, you know, so that's the beauty of doing diagnosis. And also that means he doesn't call me back and be like, hey man, it's Valentine's Day weekend. Come on down here and let's retry this motor. And if it doesn't work, All right, so speaking of transformers, we're going to talk about transformers and ignition coils, but an ignition coil is a transformer. So some transformers all ignition coils are transformers, but not all transformers are ignition coils, if that makes sense. The reason we use ignition coil is just because it's the easiest to visualize. So in an ignition coil, we have what's called the primary and the secondary. And if you look, 12 volts goes to this primary coil, and it's going to wrap a specific number of times. And it's going to go around that coil and out. So if we give 12 volts to this ignition coil primary, and then we give ground to this ignition coil primary negative, basically what it's going to do is begin to build a magnetic field. It takes a little bit of time for that magnetic field to build up. That's a thing in ignition we call dwell time. And then when we're ready to start the spark, you know the spark I'm talking about, right? It was Valentine's Day. You know that spark, that magical spark? No. Not that spark. This spark down here, this spark on the coil, on the spark plug, pow. When you want that spark to occur at the precise timing, here's what you do. Turn off the negative connection, because you see this right here was a transistor. This is kind of like a solid state relay. Remember, we covered transistors part 2. But if we cut the negative, what happens is this magnetic field collapses, and that magnetic field that we kind of made, it's induced into what's called the secondary winding. So you can just barely see there's a lot of red wires, but the red wires are wound many, many, many more. So if you had, round numbers, 12 volts, and you wanted 120 volts, you'd wind the secondary 10 times more than the primary. So they wind them in a specific number. That's going to give you the increase in voltage. Make sense? 12 volts, remember I told you it's not even enough to like shock you or give you a little nothing. That's not enough to jump an air gap on a spark plug. So what we need to do, we need to increase the voltage high enough where it'll actually go to this electrode and arc, a little lightning, a little zap, to the grounding electrode, and that will ignite the compressed air and fuel inside your engine, not motor. Make sense? Kind of. So here's how the coil works. Give it 12 volts, give it ground for a period. The second you want the spark to occur, shut the ground down. That collapses the primary magnetic field into the secondary, induces high voltage and current right there, which causes the spark. Then when we're done with that, we reconnect them. That ends the spark. We reconnect the ground. That the spark goes away, and it starts recharging the coil again. And next time we're ready on top dead center compression, we take the ground away and pow, we make it spark again. So an ignition coil is kind of magic. It takes 12 volts and it makes it into 60,000, or that's what it's saying, 60 kilovolts. 60 volts? No, 60 kilovolts. Kilovolts meaning 1,000. So if you want 60,000 volts, no problem. We got an ignition coil for you. But let's say you're in this building. We've got big high voltage power supply from Edison or from whoever you got. They're going to run high voltage, and then a transformer is going to drop it down to like split phase 120, which we call 240. Transformers can make the voltage higher. They can make the voltage lower. They can transform it either way. Ignition coils always make the voltage higher so that we can arc the spark plug. Kind of makes sense, sort of. The transformer on the power pole outside your house takes the kilovolts in, and it makes it into like regular volts. It takes thousands of volts in, makes it into regular volts, and it all has to do with the number of windings in the primary and secondary. The primary and the secondary don't touch. If they do, they're shorted. The coil won't work. We could test for that. Generally, the way that we test these coils, we verify we have 12 volts coming in. Does this sound familiar? What's the coil need to work? It needs 12 volts. It needs ground. But then what has to happen to the ground?
To disconnect.
Exactly. We can measure that. We get our meter. It should be 12, 0, 12, 0, 12, 0, 12, 0. So if you have a car that's not sparking, in one measurement, put it on the coil and crank it over. If it's not cutting the ground, you're like, hey, why isn't this transistor cutting the ground? Maybe it has an issue with the module. Maybe it has an issue with the crankshaft position sensor, right? So without going crazy engine performance, we just have to know we need 12 volts in ground, but the ground, one of the two needs to be pulsed actually. You could technically pulse the 12 volts, but we just don't normally do that. Old days, we used to use points, and the points would push it up with a cam, or like let it fall down with a cam, and then when you rolled it over, the cam would push it off, and the connector, the contacts, the points would break. They call it like breaker points. Break the ground, break the ground, break the ground. That would make it spark. That's still kind of how some lawnmower stuff works, actually. So that's your transformer. The way we diagnose it was kind of simple. We really do the diagnosis on the primary side. If your primary side is good and you don't have secondary, you're pretty much, you got a coil. You can also check the secondary, but we don't measure that voltage because it's 60,000. Your meter will be like this, like, that's it, it's done. There is a way you could do it. They have inductive testers that'll flash like a light. So sometimes they'll even beep, 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 beep. And you're like, okay, it's pulsing, cool. Transformers, not that hard. But you'll get way more into the specific ignition coils later. Transformers could be as simple as just bringing the voltage from 12 to 24 or to 48. From a hybrid vehicle that's running 250 something volts in the high voltage battery, we need that to charge our 12 volt battery. So we transform it, we convert it down. It's going to be 250 volts dropped down to 13.5, just like an alternator, but no spinning alternator, no belt. Just it's going to charge right out of that inverter using like transformer. Cool. So transformers are all over. Not a real big thing. Cool. And there's like here's that in a diagram. 12 volts coming in, ground. The second you break the ground, this electricity in the black jumps into the yellow and then is going to actually go to the spark plug, poof, and spark. Assuming, and for the record, if you don't have good primary voltage, you won't have good secondary voltage. It's almost like a, all right, if you guys go, let's say, to Mexico, you're expecting to trade in your $12 for how many pesos? 60,000, I don't know the number, right? But you're expecting that transaction deal. But if it goes the other way, if you don't show up with $12, you ain't gonna get your 60,000. If you don't show up with your 12 volts, you're not getting the 60,000 volts out of it. Makes sense? So if you have a problem on the primary, it'll cause a problem in the secondary. And then, like things in nature, there's always a cost. So I said it was magic. I kind of lied. If it takes 12 and it makes 60,000, wouldn't you love to do that with your dollars? 12 bucks? Let me trade you for 60,000. I do that deal all day. There's a negative. Yes, it goes from 12 to 60,000 volts, but it goes from 12 amps to 1/60th of 1 amp. It increases the voltage proportional to how much it decreases the amperage, or the other way around. So if you have really high voltage on the power lines, it's not that many amps, but by the time you drop your kilovolt power line down to your transformer, it's much lower voltage, but it has the capacity for a lot more amps. It's a proportional trade. Like I mentioned before, the way that science works is pretty amazing. It's like ingenious. So you want this, no problem. Proportional, fair deal. Double your voltage, half the amperage, that's the fee. 10 times the voltage, 1/10 the amperage, that's the fee. 1/10 the voltage, no problem, I'll give you 10 times the amperage. You understand? Proportion? That's what this does.
That is why power lines, when they're transmitting power,
Yeah.
they transmit at 100 kilovolts. Because if they transmit at a high voltage, you have less current through the wire,
Yeah.
so
safer.
that the wires don't overheat and melt.
Yeah.
And therefore you can transmit along very, very long distances. That's exactly why you transmit at high power, but
Yeah.
then you have a transformer at a station to bring
Yeah.
it down to 110 or 220.
Yeah, exactly.
That's exactly why they do it that way.
Yeah, so now you guys will if you can understand an automotive coil, you can kind of understand a little bit about what's going on when the transformer goes bad at your house. It's like the transformer's bad, they have no way to take your kilovolts and make it into something your house can survive. But I did have one former coworker, super smart dude. There was a windstorm and it knocked a branch or something into the transformer, and the high voltage line, the kilovolt line, fell onto the house and grounded out in his coax cable, how you have cable, and the whole house is like, it was trying to send thousands of volts through the little coax cable wire. It ended up catching on fire. It totally ruined the house. The house was shot. You can't be having thousands of volts going through our wires. They're not made for that. Same with, you can't be sending hundreds of volts through automotive wires. at that type of amperage. They're not made for that. Their insulation is not going to withstand that much electrical pressure. That's why the house wiring is a little different.
When an ignition coil fails, why does it fail?
Things can happen. So this coil right here, what if I were to snip that little wire right inside? Now there's no connection from primary to secondary. It doesn't build a magnetic field. It doesn't pulse the spark plug. So anywhere, if we have a break in these windings, because remember the windings are round and round and round and round and round and they get hot and that can cause the wire to break down. And if you get resistance inside the winding, you're going to get an undesired effect, probably low voltage on the secondary, which means your spark's going to be an or weak. If you have a weak spark, it might fire, it might not fire. If you have no spark, the car's not going to start at all. So I would start by checking the primary, and there's a little bit more detail you can go into. Like this would be a good example actually to not check with your meter. We'd put a picoscope or an oscilloscope, a non-branded oscilloscope, and you could actually look at the voltage over time and do a lot of diagnosis based on the condition of the waveform. What the waveform looks like can tell you physical things. So like, for example, if your spike on the waveform is really high, that means it's really hard for the spark to jump the gap of the spark plugs. That could be a spark plug that's got too much spark plug gap. Cool, but the oscilloscope reading would guide you to that. So that gets that's a whole class right there. So electrically, we're good. Shoot it.
The voltage coming down to the main coil, is it AC or DC?
DC, and it is DC. Yeah. Yep, DC, because that's really 99%, that's what we're using. So we're taking 12 volts from the battery, sending it to the coil, and then we're also going to the ground and taking the ground, running it into the computer, having the computer pulse a transistor, all DC.
So basically you're creating AC using the transistor, because the only way for the induction to happen is if the magnetic field continues to change.
Yeah. It is a little weird, huh?
Yeah, it's weird.
And that's why if we were to do a probe actually of a oscilloscope, this is engine performance. This is advanced engine performance, really. You could actually graph the primary and the secondary side and kind of tell like which one's causing the issue. But you'd graph it. We could do some cool stuff, really cool stuff. All right, so overall I think that's pretty good, but just know the transformer action causes heat. Again, you don't get anything for free. So over time, these tend to get hot, and heat-related failures are typical, especially if your transformer, your coil, acts up like on really hot days. That's an indication of electronics, or sometimes really wet could be an indication of like a loss of insulation or isolation. If it's got a crack in a wire or a crack in the transformer, it'll arc through the plastic to ground rather than arc the spark plug. So old cars, you're not supposed to hose them down under the hood. New cars, you can do that. I do it right now. Anybody's got a car newer than let's say 2004, we go out there, blast it off, it's chilling. You come in with a Beetle that's like a 60 something, no. I won't even run it through the car wash unless I put a big trash bag over top of the whole distributor and all that stuff, because those components were known to arc to water, and then it won't start until you come back tomorrow and it's dried out. Same kind of concept with these windings. It's not the winding, it's actually the insulation here. This is in a plastic box, and if there's a crack in the box, this could actually arc through the crack to ground rather than spark your spark plug. So still electrical, but it's electrical from engine performance, and so engine performance is very electrical based. Very. All the ASEs are at least a little. Engine performance, very. Cool. Step down we talked about. Step down goes high voltage to low voltage, but you get increased amps. Resistors. You could be a resistor right now, because this is a tough lesson. This is hard. You could resist me. You're going to resist the flow of knowledge into your brains. And you're welcome to do that, but I'm still going to try to provide it. So normally fixed, variable are nice and commonly used for sensors. So if you see a variable resistor, that's probably varying due to a position. Like if I put a sensor on my elbow, maybe this is 1 volt and this is 4 volts. What's this? 2.5, yeah, or 2, yeah, 1, 2, yeah, exactly 2. Bingo, middle would be 2, 4, 2, 1, 2, 4, or 2.5, whatever. So that can tell you position, cool. But also We can use a variable resistor to measure temperature. We mentioned it in the second day. Thermistors measure temperature. So if you want to know the temperature outside, so you can calculate your AC performance or your air-fuel ratio, or how much fuel you need or whatever, we'll put a thermistor, which is a variable resistor that directly indicates temperature. I'll show you. Cool, so if you look, this is what it's saying. Linear, where resistance value varies proportionally with movement or temperature. So what it's saying is like, it's very precise. It's like, this would be, was this 4? This would be 4.0, 3.9, 3.8, 3.7, 3.6, 3.5. So you could tell, and it very evenly goes down to 1 volt. 1.1, 1.2, 1.3. So these resistors change resistance very proportional to the movement or the temperature range. Negative 40 degrees could be, actually that'd probably be OL. That's open circuit would be negative 40. If you were to have no resistance, that'd read about usually 270 or 300 something. Right in the middle would be right in the middle of that range. If your sensor reads negative 40 to positive 340, what's the middle number? 140? Yeah, 140, right? So 140 would be like middle resistance value. A lot of resistance would be really cold. Very little to no resistance would be very hot. And so we can measure the resistance and therefore determine what the temperature is of whatever. What do you want to know the temperature of? Tell me now. This room, that'd be an ambient temperature sensor. How about the desk? You could put a contact temperature sensor. How about your blood? We could put like a coolant temperature sensor and thread it into your arm. You'd probably die. But we could measure the temperature of your blood, the car's oil, the car's coolant, the car's transmission fluid. Don't you want to know if your transmission's overheating? Good. Put a temperature sensor in there. And then you can put a gauge, right? So that's how we do that. We use a variable resistor that indicates temperature and can read out on a gauge. Or in more modern times, we may not give you the gauge because we think you don't know what to do with it. So what we'll do is we'll have that be an input to the computer, and if the computer sees it gets too hot, the computer will go into like a self-protection mode. Makes sense? So we have lots of temperature sensors in lots of different components. Cool. And they all use the fixed to the variable resistor layout. It's called a voltage divider, which I show you actually in an engine performance related video. Cool. So this is the resistor. All right. Remember my arm? It would not normally go to 0 volts. It usually goes close. So my arm all the way down might be like 1 volt or a half a volt. Then if I'm right here, 2.5 volts. Then if I'm right here, maybe 4.5 volts. Make sense? This is how it does it. It sends 5 volts to a reference. It sends ground to here. And depending where my arm's position is, it'll come back anywhere between 5 volts and 0 volts. But they limit the travel. So it should never actually hit full 5. It should go as high as 4.5 maybe. And it should never go as low as 0. It should go maybe half. Cool? And so if you want to know the position of my arm, you measure the voltage, and this is the sensor, 3 wires. Let's just say your sensor's not working. You have no idea where your arm position is. You come here. Does it have 5 volts? Uh-huh. Does it have ground? Uh-huh. What is the variable voltage? Anybody know what we should get on that one? Somewhere between 2.5 if it's right in the center, exactly. And then if it's down here, it's probably going to be more like close to 0. And if it's up here, it's going to be close to 4.5. So you'd make a measurement here and see if it correlates with the position. So a throttle position. Wide open throttle should be 4.5 volts. If I go, hey, Tony, how you doing? Put your foot on the gas, Tony. I better get 4.5 volts. And if I get 0, I'm like, oh, that's weird. It's got 5 volts. It's got ground. Why is this one not reading well? Maybe because the sensor's broken inside. Cool. So we could do an electrical diagnosis of that right then and there on the spot. Cool. That's of a potentiometer. That's a 3-wire, and the voltage varies between high and low depending on the position. Cool. Shifter position. You name it. What else do you want to know about those? Doors. Windows if you really wanted. They don't normally track windows that way, but they could. Cool. So here's the diagrams. This is a fixed resistor. See, it's just a straight zigzag. Variable has the arrow through it. That means this resistance will vary depending on the position. You get me? A little bit, kind of. This one will vary depending on the what? Exactly. So this resistance may be a little, but as it gets hotter, actually, let me go the other way. This resistance may be a little, that would be showing full hot. As it cools down, it should get more and more and more proportionally smoothly. If it's going with like 100,000 ohms and all of a sudden it's at 10 ohms instantly, no, there's something wrong right there. It should be proportional to the temperature. They actually have charts where you can test these. Are you going to test it in this class? No, probably not. You could actually on the board if you wanted, but really, I need you to understand this electrically. Remember, the resistance changes the voltage drop. So as the temperature changes, it changes the voltage drop because the resistance changes. So therefore, we would have to diagnose it electrically like that. Or go ahead, just parts can and shoot one in there. If it fixes it, you're good. If it doesn't, you just say like, that one was bad. You need another one. Try one from O'Reilly's rather than AutoZone. They'd be like, oh, the O'Reilly's one was just as bad. We need to get one from OEM. You know, when somebody's giving you those stories, you know what it sounds like? They just don't know what they're doing. If you know what you're doing, you're not guessing, you're measuring. Cool. That's pretty good right there. Now a little bit on resistors. Like I said in the intro, I don't really remember these, but just to make sure you know, this is going to have a specified resistance, which you could code by the band colors. Or what I would do, you can measure it. The problem is you'd have to, like if you take a measurement on a resistor, how do you know if it's in spec or not? You'd have to determine the spec. So if the resistance was 25 ohms, plus or minus a quarter of an ohm, don't you give this away. This is an activity. What is the range? By the way, automotive's not perfect, okay? It's plus or minus, it's a range, okay? So if I'm saying it's 25 ohms, it should be 25 point what? 0, 0, 0, infinity and beyond. It should just be, it's not gonna be perfect. I'm just telling you right now. So if it's 25 ohms plus or minus 0.25, let me word this in dollars, cool? I'm gonna offer you $25 plus or minus a quarter. What's the range?
25 or 75.
All right, so here we go. We got 25 in the middle, 25.0 plus a 0.25. That was the spec, right? So that's 25.0 plus 0.25, 25.25. Do you agree? 25 and a quarter. Do you want to feel better? How you like that? Now, what's on the other end down here? $25 minus a quarter. 24 3/4. Okay, if it's in that range and we measure it, resistor good or bad? Good. Bing chillin'. That's the lesson. I don't use these so much, but in the service manual, if you're testing a coolant temperature sensor, it'll say test at 72 degrees and it should be 10,000 ohms plus or minus 1 kiloohm. That means 10,000 minus 1 is 9,000, plus 1 is 11,000. Oh, okay, so 9 to 11. You have to come up with your range. Make sense? You do it just like this. Yeah? Yeah? Yeah?
So this would be almost the same as like the thermostat inside of water heater?
I don't know about all of them, but yes, I'm betting you that if it's a more modern style, it's probably a sensor, it's probably a thermistor. Sometimes they're switches though. Sometimes they don't give you a resistance. Sometimes they're either open or when it gets the right temperature. Maybe when it gets cool, it closes, and then when it gets hot, it opens, and that's why they cycle. But the newer ones, I guarantee you, is going to be a temperature sensor because they're using little circuit boards that's like a basic computer. Oh yeah. Go ahead, Priscilla.
So all the resistors all of them are going to be that range?
No,
No, so
that was only because this band.
Oh, okay.
So if it was, we'll do another one for fun.
Okay.
Let's go with the resistance is 100 ohms. How about that? Plus or minus, let's do a 1.5 ohms. Cool. I like to do these diagrams where I do it like this. Right in the center is 100. So what's 100 plus 1.5?
101.5.
Bingo. You got it?
Yeah.
Okay, 101.5. Now what's on the low end?
99.5.
No, that'd only be a half. If it was 100 and it went down to 99.5, that'd only be a minus a half. It's minus 1.5.
So it's 98.
98.5, exactly. So see, that's where it's not real rocket science, but it's like if you do sloppy math and you're like, oh, it's supposed to be 99.5, but it's 98.5. That thing is no good. I fixed it. It's like, wait a minute. Actually, it was good. So if you replace that, it ain't gonna fix nothing. And then you're doing the walk of shame. I put the part in it after you called the customer, and the customer's like, oh, that's all it is? It's just one resistor? I'll buy it. And then it didn't fix it, and then you're like, I don't know, we need to take more money from you. You mechanics are crooked. You're unethical. There is no such thing as an honest mechanic. It's like, look, I made a simple mathematical error, and that's why my mind automatically goes to, people just don't know enough to be able to fix these cars. Maybe some people are ripping them off. But I'm gonna kind of like focus on this. I can't really focus on that. I'm gonna say, if I can get you really good at this stuff, you'll have less of those embarrassing walk of shame, call the customer back up. Yeah, I've had a few. I graduated the School of Hard Knocks, but actually I'm enrolled in like the permanent program. I'm stuck in there. Keep waiting to get my thing and don't you do this with, I don't even know, I've graduated from 3 different schools, but don't you do this or something? I don't even know. That's been the more valuable school. Okay, you guys know it's rated in ohms. This is the Omega. Cool, we talked about that in the beginning. You're probably pretty good. Okay, and here's a breakdown in case if you're really interested in this, you can figure out what the number is. There's even little calculators online. You can just type in the band color. It'll spit it out. So that's what I would do if I had to. However, what we do, generally, we don't test these. You may test a coolant temperature sensor. Let me show you what that looks like. Here. Or ECT or IAT, engine coolant temperature or intake air. We're gonna be testing these at these terminals here. There's no bands and colors and stuff. We're not, I haven't calculated those colors since I was literally in your exact shoes. And they're like, here, figure out these things. And we spent like the whole class and never, ever, ever, ever did it again, ever, never. However, the cars come in, I need to be able to measure this resistance and compare it. Cool, so we work like this. We're checking these couple terminals. If you were to do like electronics repair, yeah, maybe you're like, oh, let me go inside the ECM and test individual resistors that are inside one by one and find the bad resistor and like desolder it out and desolder it or something. Not what I do. Maybe more like you.
No, you only do this when you're building boards or you're repairing boards.
Oh, I see.
Beyond that,
I see. So if you had a board that had a bad resistor and you rolled onto Radio Shack 20 years ago, you'd be like, give me this resistor and solder it in.
Yeah.
Yeah.
That's about it.
Not my area.
No.
But cool to know. Good for you to confirm it. It's not real common I have any sort of electronics engineer in my presence, so I like that. And if I'm ever wrong, I'll eat it too. If you were to be like, hey dude, you are so wrong, I'd be like, really? But that's why it's easy for me. If I'm wrong, I just abandon it. I'll be like, oh dang, I screwed that up. Move on. Now I'll do it right. I was pretty sure I was right, so you're helping me feel good. All right, and so fixed resistors, that's what we're talking about. There's tons of them built into the circuit boards. The rheostat you showed, and the potentiometer, I just want to separate these. A rheostat is like a variable resistor, but it's designed to carry power. Okay, this is something that you're going to screw these boards up. They're probably already screwed up. This is designed to be a dimmer. It carries actual legit current, like several amps potentially. It's a potentiometer. It's a true rheostat. So you send 12 volts in. This consumes 6 volts. You get dim bulbs. Remember, February 14th. Right? The noise. Everything is better when And then if it's more like a sensor, that's a different type of thing. So let me jump right to here. A potentiometer doesn't carry a lot of current. It's very small. Potentiometer is a sensor that measures position. They look the same. They have 3 wires. If you send a lot of current through a potentiometer that's a sensor, poof, magic smoke is out. It's junk. Make sense? So in those kits where we build electrical components, if it's a potentiometer and it looks more like a little easy to move, light duty, small circuit switch, don't try to put a major amperage through there. Don't put that in the circuit as a dimmer. That's how they die. You understand? I'll even give you a new term. This right here, potentiometers don't die. They're murdered. All right? They probably got murdered. It probably did. Okay, now back it up. Here's how we're checking the rheostat. We can actually put our meter on there and cycle the different resistance. As we turn it, it should go up and down. You'll actually see low resistance, high resistance, low resistance as you move the knob. Look at this one. OL. Turn it up, OL. What's wrong? Yeah, it's junk. It's no good. It should never have OL all the time. It should have low resistance to high resistance. If it's OL, it's open internally. This one's no good. All right, the way we do the potentiometer is similar, but we're not jumping 12 volts to it. The computer is sending small current. It could send 12. Most of the time it sends 5, actually. And we're just going to check 5 volts. Look, we got 5.141 going in. That means the reference voltage is good. It's not 12 volts because these don't have to work on 12 volts. A lot of time we chill it down to 5 because this is sensitive, more like light duty electrical. Cool. And then we could check the ground, which should read 0 depending on how you're testing it. Remember I showed you that trick. Like if you put your positive lead on the battery and you put your negative lead on the sensor ground, it should actually read source voltage 12.6. But if you were to leave your positive lead on the 5 volt reference and put your negative lead right on the ground, it should actually read the 5.144, whatever's on the last page. Cool. That tells me those two are good. The last test, I got to check that middle one, and that's the reference. And do you guys recall why that changes? That's at 2.4. What's that mean my arm's doing? Right here. Yeah, it's half. Exactly. And then if this is a throttle and I open the throttle, it should go more to like 4.5. And then if I close the throttle, it should go more to 0, right? And you can watch it be really smooth. If it's jumpy, it's no good. If it's like 1.5, 2, 2.5, 0, 3, you're like, what the heck was that? That's an open inside of the sensor. That sensor is no good. You found your problem. Electrically. Cool. And then capacitors, a capacitor, remember that's a thing that's an inductor. So if we were to go back to the airbag thing, we put the capacitor in the circuit. While we're running the car, the capacitor charges up. You want to make it about the boom boom, the jiggy bump system? We could do that. There you are. You jump in the car, you fire it up. Your alternator's charging the battery. Cool. Your capacitor is also like, give me some of that. 13.5, 13.9, give me that. Charge the capacitor. And then all of a sudden, what happens? The beat drops. Am I right? Boom, 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 boom. It blows the license plate off. The glass blows out, right? That takes a lot of power. Your capacitor spent its time grabbing the energy when the getting was good. It's like a savings account. And then when it's like, hey, we're going to make this beat drop, we really want to attract a mate, and this is how you do it. You blow their eardrums out, you ding dong, boom, and it gives all the electricity back, and that's when it hits. And they're like, that's it. It's Valentine's Day. We're done. Penguins for life. Am I right? All because that capacitor. I tell you, that's how serious this business could be. That's a fun way. The more factory thing, we do capacitors in a lot of different ways, but the one I was telling before, the airbags, you lose power. Well, the capacitor spent all its time grabbing that savings, and now that the power died and you're about to hit the guardrail, it really went in a bad way. You like the last story, but you're about to hit the guardrail and it's like, hey, we just detected a rapid deceleration. Those capacitors could be keeping your computer awake and also give enough power to ignite that, to give 12 volts in ground to the squib in your airbag, which starts a chemical reaction, which makes a big fluffy pillow that's made of fiberglass, and chemical burns your face into your face. Poof. Makes sense? So we need capacitors to give the appropriate amount of energy as needed. So they're rated in capacitance. So that could be the charge stored and the potential difference. And they'll do the math and say, like, we need this much power to keep the computer awake. We need this much power to deploy this airbag, that airbag, the other airbag. And then poof, kind of makes sense? That's mostly where capacitors are helpful. Now, why is that important? Y'all gonna work on some cars. Cars have airbags inside. You probe the wrong thing, you deploy an airbag. You're gonna find out. Remember the big fluffy pillow made of fiberglass that chemical burns your face, blows the windshield out of the car, rips the seats open? You are not gonna wake up feeling good the next day. I'm gonna let you know right now. So what we're gonna do, we're gonna follow protocol. So if we're working on airbags, there's actually a power down procedure. Usually it's just disconnect the battery. Sometimes it's pull the fuse for the airbag system. Then it's a waiting game. How long? Depends on this type of stuff. How much electricity is stored. And inside there's little resistors to drain them down once you remove the power. Sometimes it's 3 minutes, 5. On hybrid stuff, it could be 15 for the full high voltage system. So that's why you need to know capacitors. Capacitors are what power the system when there's no voltage present. So if you yank the negative terminal off, you think you're chilling. I don't know. Those capacitors still may have enough juice to, you know, to squib. Cool? Okay. I hammered you with everything I had on this one, but we got a part number 2 for next time. Let's go ahead and we'll do a full stop on that.